important point. First important point from the introduction following on my thesis is basically the connected car vehicles. So currently, as we know, in the automotive industry, there are basically two types of revolution which is undergoing. One in the terms of the electrification of the vehicle platform, and the second in terms of the connectivity. The connectivity, what we speak here is not merely of hardware connectivity, but also for enhancing the user experience as well as the driving experience. So what we talk of here is the connectivity of the vehicles to the external services and also while receiving and sending the data. It can be in the form of interface awake infrastructure, or it can be with the other vehicles, or it can be with other devices, or it can be with other pedestrians as well. Now, the importance of this connectivity is shown by this forecast. For example, as predicted by Juniper Research, we are expecting around 367 million vehicles to be connected. And this shows the importance in the terms of the industry standards. What we get out of the benefits is basically we create new revenue models inside the industry, around $750 billion. And also we improve the mobility experience, and also we enhance experience using driver assistance as well as predictive maintenance. But there are concerns to this benefits as well. The cyber attacks are amounting to 10.5 trillion, which is much more than the benefits that we can perceive. And also there are security problems as well as privacy issues because the data which is generated is very huge. And also the data infrastructure scalability currently is also much more limited. So how do we implement this connected car communication? Will it be through centralized systems? Like for example, centralized systems, as we all know, like we have a client, multiple clients which connect to a centralized infrastructure like a server. Or it can be a cloud network which has much more better fault tolerance, like we have distributed servers connected, and also multiple clients can connect, and it can be scalable. But the problem in this, even though it's distributed, the problem is data censorship, and also the trust and the transparency of the data is lacking inside a single entity. So the solution, what we can perceive is basically decentralization. Decentralization, even though, for example, we can look at three entities here. The three entities are interconnected, all the servers are interconnected, and all of them have a redundancy of the data. They agree on the data structure, and they agree on the diffusion of the information. The clients can connect to any of the servers which belong to any other entities, and then it can get the information. What we get as benefit is basically the collective fault tolerance and the data ownership and censorship resistance, and also the trust and transparency in the data that is diffused. So more about decentralization, like how do we implement this decentralization? So we have known as DLT technologies, distributed ledger technologies. The process starts with the very simple transaction initiation by a client, and these transactions are packaged into a data structure. And once this data structure is constructed, then we subject it to a consensus process. Consensus process is basically agreeing on the data structure, verifying and validating it, and then reordering it in case of multiple transactions. And then we store in a finalized structure, a DLT structure, which can be a blockchain. Basically, the structure of the blockchain is basically the current block refers to the previous block's hash. So it constructs a chain process. So we are not limited only to blockchain as a DLT type. We have multiple DLT types. For example, based on the structure, we have blockchain has to have data acyclic graph. Based on the governance, we have permission and permissionless based on the authorization of participation in the network. Based on the layers, we can start with the base layer, which is blockchain. And depending on the base layer blockchain, we can construct multiple layers on top of it for faster transactions, even though this layer depends on the layer 0 for a single source of truth. This is a single source of truth, and other layers are built on top of it. Now, let us look at blockchain versus DAG. Directed acyclic graph is basically a graph which consists of edges and vertices, and the edges represent the relationship between the vertices. Vertices consist of transactions or a block of transactions as well. So when a new transaction enters, it basically attaches to any of the vertices here, and depending on the network, depending on the connectivity of each vertex connected, the old vertex, it decides the finality of the transaction. Decides finality of the transaction. The good point here is basically it is scalable compared to a blockchain, but the bad point is basically like we are subject to a lot of immutability attacks on the DAG. And the blockchain, as earlier discussed, it has much more security, and also the smart contract layer developed is much more mature compared to DAGs as we have tested. So talking more about DLT types, how do you make a DLT type blockchain more intelligent to cater to the needs of automotive industry or for any other use case? So smart contracts. Smart contracts are nothing but a piece of code which resides in a blockchain at a particular address. And then any party can interact with the smart contract to execute a certain set of transactions. And the execution of the transaction depends on a certain set of conditions which are written inside the smart contract. And once the transaction is executed, it depends on an external VM. So all the transactions are first decoded and then executed on the VM and then tested and verified and then stored back to the DLT structure. In case of Ethereum, as we can see here, it's an example of a Solidity smart contract similar to JavaScript. The next one, another example is basically Substrate. It's based on a Rust. It's a Rust smart contract. It's another example which utilizes a WASM virtual machine. But what is integral to a blockchain process? To make it more intelligent, yes, but what is integral is basically consensus. Consensus refers to a process by which nodes agree on a common state or a data. And as you can see here, it's similar to a network OSI layer model. Like consensus layer stands at the middle and it orchestrates all the actions inside a blockchain. For example, the data layer and the network layer. All this send the transactions and the blocks to the consensus layer, and the consensus layer verifies and validates the transactions. All the other layers, the applications that we can build, depends on the finalization of the transaction in the consensus layer. But as I mentioned earlier, consensus refers to the agreement, and the agreement between nodes can vary depending on the network model. So more simpler network model that it's an idealistic case, like real world distributed systems. For example, a synchronous model, where there's a known upper bound, but we cannot expect it to happen in the real world. And the next one is asynchronous model. It is the very hard model where there is no bounds, and basically there is no deterministic protocol, consensus protocol, which exists. And even there is one fault process inside the consensus, there can be no consensus which can be arrived. And the next one is basically what we interest more is partially synchronous models. Partially synchronous model is comprised of synchronous time periods as well as asynchronous time periods. It has a finite bound time and global stabilization time. Global stabilization time is basically the time needed for a node to recover back, basically the partial fault tolerance time period. And the message sent at X can be delivered at delta max of X and G, global stabilization time. And the good thing to note about is it can tolerate up to 1/3 Byzantine falls in the case of the message which is not secure. In the case of message which is secured by cryptographic means, then it is just 1/2 honest participants which is needed, and can perform in linear rounds, as well as the communication complexity is quadratic. Now, so we've talked about the introduction revolving around my thesis. Now let us look at my thesis objective. So these objectives basically to evaluate and enhance the consortium blockchain technologies by focusing on consensus algorithms for connected car communications. Here, I would like to precise a point, like what we mean by consortium is like authorized mutually benefiting participants, but guaranteeing security, privacy, and scalability. And also, we concentrate on layer 0 blockchain, which is the underlying, the base layer, and we target it to have consistency, availability, and partial tolerance. So this thesis was performed in the context of Smart IoT for Mobility project, which is a project which was held by LIAT, as well as partners with Renault and Assurance partners. So let us talk about my plan of the contribution. So I started with the first one, the evaluation of the BFT consensus, which is, although the BFT consensus is quite vast, the state of art, I concentrated on the most consensus algorithms which are implemented in real blockchains. And it was followed by a theoretical assessment. And then we implemented, tried to solve the mobility use cases and evaluated those use cases, basically from a consensus point of view. And then we faced some issues while implementing the mobility use cases. So we wanted to ascertain whether the issues that we had faced is really valid. So we had to test it on a homogeneous simulation platform. And next, having verified those challenges, then we try to solve those challenges by proposing a new algorithm called Cuba. And then we follow it by conclusion and perspectives. So let us start with Byzantine fault tolerant consensus algorithm, the classical algorithms. So Byzantine fault tolerance algorithm refers to the problem where the processes try to agree on a particular data or state, even though there are malicious participants. And also the message communication between the participants can be lost, delayed, or the good thing is eventually delivered. So even in these hard conditions, there has to be a consensus which has to be reached. The first solution to this problem was proposed by PBFT, by Lamport, Mr. Lamport, and it was implemented in Hyperledger Sawtooth blockchain, which is enterprise blockchain. So it starts with a node being selected as a leader in pre-prepare phase. It emits the transactions, and then the other nodes, follower nodes, then reply with the prepare message. And once the threshold is reached, 2/3, it then proceeds on to the commit phase, and then it is considered to be finalized. For a new round, that is for progression to the new block, we need to select a new leader using a round of view change. As you can see here, all these are there is a high communication complexity, but the good thing is there's redundancy of message communication, which ensures that there is consistency and there are no forks in this consistent algorithms. And close consonance is like we have two algorithms which are basically inheriting this aspect, but with a slight change as well. For example, you can see here, this is Istanbul Byzantine fault tolerance. These two are implemented in Ethereum blockchains. The change is basically the round of view change happens only in case of failures. And also it does not wait for the prepare phase to be completed. It directly goes on with the commit phase, which can introduce two blocks at the same height, two duplicate blocks at the same height. For this, they implement a block locking mechanism to ensure that only one block is produced at the particular block height or block round. Quorum Byzantine fault tolerance, since they try to put in a block lock here, they try to resolve this. It's by the same developers. They try to resolve this by removing the block lock mechanism and ensuring that they finish, prepare, commit in sequential phase. And also the round view change is much more lighter. So these are most of the classical algorithms which have existed in Hyperledger Sawtooth and Ethereum. And next we consider some algorithms which are lighter compared to with lesser message complexity, but show better performance. For example, here we note Aura. Aura operates in terms of time periods. For a time period, a block proposer is chosen. A block proposer is chosen how? Based on modulus operation over the total number of nodes. And then he proposes a block, and then the block is accepted by the remaining participants. But the good thing, it is implemented in parity Ethereum as well as Substrate. But since it's based on time periods, it is subject to a lot of synchronization problems, and there are a lot of forks which are created. In close similarity is Babe and Click, a blind assignment for blockchain extension. Here, the block proposer is chosen based on verifiable random function, which is a function which is similar to the proof of work, where we calculate the hash lesser than a threshold. It's similar to the, there is a computation complexity here, which obviously needs us more synchronization between the nodes. And obviously, this is prone to lot amount of forks. Click, it's more light variant. You have a single phase, the block proposer is done, and it is then accepted. But if in case this block proposer fails, there is a backup proposer who also proposes a block. So it also introduces forks. Forks are basically duplicate blocks at the same height. Basically, in-order proposer is the proposer who is legitimately selected. These are fallback proposers. This is implemented in proof of authority protocol in Go Ethereum, and this is in Substrate, and this is in parity, and as well as in Substrate. Both are all are Ethereum protocols. Okay, now let's look more about forks. What are forks? Forks are basically like, as you can see, the black boxes here are the finalized blocks. On top of these blocks, we have created multiple chains which exist. The multiple chains are basically forks at this height, and me to resolve the forks, which is basically done by another algorithm, consensus algorithm known as Grandpa. So the Grandpa works along with Aura and Babe to resolve the consensus, basically to resolve the forks in the chain. So as you can note here, the ones are denoted by the primaries and two are denoted by the secondaries. Primary, basically the legitimate proposers, and the second two is denoted by the secondary. Two is denoted by the secondary or fallback proposers. So how the protocol works is basically it selects the largest chain with the most number of primaries. As you can see here, this is the largest chain with the most number of primaries attached to the finalized block. So how it works is basically like, to precise, this works on a chain of blocks, not on a single block as the earlier protocols. So here a primary is selected, which broadcasts the block height, and all the other messages then follow a pre-vote and pre-commit phase in order to select the particular subchain. and then they finalize the consensus protocol. So let us look at the mobility implementations based on these consensus algorithms. So the first implementation is basically data certification problem. It's a simple problem, but it has an immense loss. In Europe alone, 5.6, 9.6 billion euros. But there exist centralized solutions. For example, in Belgium, there is CarPass, which works perfectly fine. But we would like to understand and work around some issues surrounding data security, privacy, and traceability. That is the main concern. So, and the focus of interest is basically, we would like to test the Ethereum consensus of EBFT, Istanbul Byzantine fault tolerance, or Quorum Byzantine fault tolerance, and Click, and also hyperlight sawtooth of practical Byzantine fault tolerance. We would like to understand the smart contract deployment process to make it more intelligent, to cater to the needs of call blocking. And also, we would like to test with non-fungible token data certification, because there were earlier solutions which existed with hash registry approach just for storing the odometer hashed data on the blockchain. And we address the privacy concerns in terms of GDPR and CCPA regulations. So how do we implement this? Basically, vehicle consists of 3 sets of contextual data: odometer values, GPS, and speedometer data. For each particular journey, what it does, it basically correlates with all this data. It verifies if the trajectory completed is exactly perfect. And then when it is perfect, it then sends via an API. Basically, the API communicates with the blockchain. And the blockchain, basically, it is a consortium blockchain consisting of OEM partners, the government partners, assurance partners. And it consists of 3 smart contracts. Basically, what it does, the main contract is just nothing but an interface to transaction and wallet contract. Transaction contract, it receives the incoming transaction. It verifies the transaction is incremental in fashion. And then it deposits NFT tokens inside a wallet contract attributed to the vehicle. So basically, for each trajectory completed, certain amount of kilometers, it deposits certain amount of tokens inside the wallet of particular vehicle. So, and also there's a certain amount of validation to be done by the admins of this network. And the user can then retrieve the account balance, and then he can get a certificate of the mileages acquired. So what we achieve here, basically, we have inter-smart contract validation, data pseudonymization, where the data of the account can be removed. In case of in case to address the GDPR concerns, try to forgetting. And also there's no external database which is used, and no off-chain components as well, which simplifies the structure, and no contextual data in spite of processing. None of them leaves the network. So we encountered some challenges while implementing this and while testing this consensus algorithms. So we wanted to, which I'll talk about later. But so we try to solve a newer use case with a newer blockchain with a newer set of consensus algorithms. So this is basically a data monetization problem. It also presents an astronomical value. It's $6.91 billion. Basically, it's crowdsourced localization. What we do here is basically like using blockchain, we try to connect the vehicles and the radar OEM partners, basically to sell the data. The vehicle OEMs can sell the data as what is the data? Basically, the radar signals and the location through blockchain, and the radar OEM can get this data from each of the vehicles. They process this data and they offer it back as an HT map to the vehicles in order to enhance the driving experience. What the HT map basically, it contains the relative position of the objects and the other vehicles in the particular location. So this is what is a fundamental concept in virtuous data monetization cycle. So our focus is basically to test hybrid consensus of Hora and Bay with Grandpa. And a smart contract is built along with the binary. It is not deployed as an Ethereum. And off-chain code is also inbuilt and secure. It's not via an external API that resides outside the blockchain normally. So this is much more secure, which presents a difference. In terms of implementation, like we have first one, the radar OEM who sends a data demand. All this is events and transactions, balance of transactions and events. For creating an asset NFT, vehicles can consent, and then a bidding process is done, encrypted bidding process done between all the partners for agreeing on the pricing, and then an escrow transfer happens, and then the transaction is initiated. So then the vehicles start collecting the data. They send all the hash certifications to the blockchain, and then once the radar OEM can access this data, it then sends a review back to the blockchain. And once the review is perfect, then the bid is completed. That is, it means that the escrow transfer happens from the escrow happens to the transfers the amount to the vehicles, as well as transfers the bidding commission, the commission to the vehicle OEMs. So the same sense happens for the HT map offered back to the vehicles. It's the same sense. What we achieve here is basically fairness. Like everyone who participates gets the benefit. The OEM, the radar OEM, the vehicle OEM, the vehicles, they can monetize the data and get benefits. And there's dynamic pricing because of the review process. We augment the token value. Interoperability, Substrate allows to be interoperable with other chains as well as off-chain components. We have enhanced the privacy in terms of encrypted bid, as well as the bid is sealed. And also the data which transfers here is concealed. And also it's account synchronization. And all the transfers here are based on a certification of the data. And there's accountable reputation in terms of review process. And there's a balance of events and transactions here. So how do we test this? We use Kubernetes cluster, which is basically a task cloud infrastructure service based in Sofia, Antipolis. We have a total worker nodes are 3. And in this worker nodes, we create through Rancher, we create a Kubernetes cluster, we create pods. And in each pod, we host a Docker container, which represents a blockchain node. The blockchain node communicates other blockchain nodes through boot nodes, and then orchestrated through using a master node. Master node basically it deals with the configuration of the blockchain, and also it starts the test, and basically it receives the information, which is then displayed on stored on InfluxDB and displayed on a Grafana dashboard. So what we try to test here is basically with variable number of participants, scalability, that is, and variable input transactions. We measure here throughput, finality, and scalability, which is the most important metrics in the consensus program. Basically, throughput is basically the number of transactions which are validated and finalized. Finality is the transaction which are finalized should not be prone to forks. And scalability is to accommodate more number of participants and see the transaction rate or throughput in the system. So let's start with the results. First result is basically PBFT. PBFT is represented by high communication complexity. It represents a low throughput transactions per second. Here we can see also we have encountered certain binary issues in Hyperledger Sawtooth itself. Like for example, the transaction processor, which receives all the transactions, has a bottleneck. The binary development issues and also the Dockerized modules within the binaries create issues because Python is not it's an interpreter language. And the second one, what we notice, Babe. Babe is not a good choice, as we have earlier remarked. Babe creates a lot of synchronization issues and forks. And Aura also creates a lot of forks. So as we can see here. And also next we have eBFT, much better than PBFT, but obviously a block locking mechanism problem. QBFT is better than eBFT, but the best among them is Click, which is an acceptable one for mobility use cases. But the problem is it is subject to a lot of forks. And also along with it, we have a lot of binary issues in case of Ethereum, that is Geth, that is the Click algorithm. For example, in case of smart contracts, there is transaction stalling, there is JVM errors. And also for separating the private from the public networks, there is an EIP 155 that is basically a proposal, which the public key recovery is a problem. And Kekak hashing, which is used by the library Bouncy Castle, also has a problem. And also during the entire test, for all the blockchains, we noticed synchronization problems, network issue, database corruption, consistency, and deadlock. So, but the only thing that we did not simulate here is basically the security point of view for each of the consensus protocol. So we have some issues here, but we are not sure if these issues are valid. So what we want to do, we wanted to test all these different heterogeneous protocols in a homogeneous platform on a homogeneous development binary. But we tried to look at the literature. What we had was basically it lacked modularity, open source availability, because most of them lacked open source and most of them were available for proof of work or proof of stake, which is not a cup of tea, because we want to concentrate more on classical BFT consensus algorithms. The other issue is basically the simulation was done using network framework with artificial estimated delays, which could create bias in the network. And also the network infrastructure, the cryptographic protocol, all were abstracted. So there was no concrete implementation, and we were motivated to develop our own simulator. Our simulator was based in Java. It consists of a cryptographic module, basically to deal with the encryption, decrypt signature, and API to receive and exchange information, and chain module basically to create the blockchain structure, the block structure pooling, and network, basically the socket communication between all the nodes, and topology generation and maintaining of the transactions in the queue. And consensus basically to infuse a protocol and basically handle the messages and also stock the messages. And then node behavior basically to have the nodes send the transactions and they maintain the private and public keys. But one thing what we'd like to precise here, basically the database used in blockchains are basically key value pairs like get level DB, but here we use runtime memory. Transaction payload is not smart contract because binaries were tested using smart contracts. Account maintenance is not handled here because we wanted to abstract others and focus only on consensus algorithms here. So, but and the others, it was UTXO. Encoding and decoding, others were RLP, recursive length prefixing, but we did not concentrate. Encryption, decryption was much simpler in our case, like RSA, and the other one was elliptic curve and hashing, etc. SHE-256 compared to KKF hash. So we wanted to focus only on consensus algorithms in first place. So what were the results? These were the results of the simulation. As you know, PBFT is the least performant. And then we have EBFT, QBFT, and then click is a better performance as represented by its phases. It represents a similar result. Compared with the binary result, which we can compare for each of them. All the algorithms, as represented earlier, the difference in terms of development creates these issues, but overall, the behavior of the protocol is assured here. It presents the same problem of scalability, even in the absence of malicious actors. And also there were consistency issues and liveness issues. So having faced all these challenges, we wanted to propose our new consensus algorithm, which is named contesting utilitarian Byzantine agreement. Basically, the philosophy is like we had certain philosophies that we built on top of it, like intellectual democracy, like where each node tries to know about its surrounding. Basically, it tries to represent a value score to others in order to maintain the equilibrium in the network. Right? And this score is basically in terms of utilitarianism, like the greatest good for the greatest number, like each action, like each proposal, a commit or signing of messages is counted in order to ensure the liveness, consistency, partial tolerance. And next, panopticon is basically the nodes to surveil other nodes in order to ensure that they're self-correcting in nature. Basically, we do not trust the nodes, we depend on its score. And Sisyphus coefficient, we only consider the scores in the recent epochs or recent block rounds, rather than comparing it to the older ancient history, because to be more relevant and to be more fair. And Swarm instinct, like we evolved the network based on the utilitarian score for each epoch. Like epoch, what we mean is a certain, like in a block proposition, we have rounds, each round takes a block, but an epoch is basically a collection of rounds where we evolve the network. Let us look at the algorithm. It starts with transaction processing, where we have the organization in terms of quorums. And the quorum, each quorum, basically it is to parallelize the network and pipeline the transaction processing. Each quorum basically creates a partial block, and each partial block is filled in order to complete a full block. So after the transaction processing, what it does, we follow it by intra-quorum competition phase, where it consists of a leader and as well as two competitors, basically proposing blocks at the same time during propose. And if the block which is broadcasted fully and accepted by all in the network, then it proceeds to the commit phase, and then the block proposer can create the finalized phase. And this is just for the partial blocks, and this partial block is stored on the ephemeral chain. And then once all the partial blocks are received for a particular full block, all the partial blocks are filled, then a block proposer is chosen among the entire quorum to propose the full block, and this is considered to be the finalized chain. It is stored on the finalized chain. This completes the blockchain process. The other thing what we'd like to know is, like, each node communicates with other nodes in terms of heartbeat messages at particular time intervals. Basically, the idea is to increase the liveness in the network and to make sure the nodes are active. So next one is utilitarian score phase. Once when the blockchain consensus process is finished for a particular round, we look at the blocks and we calculate the utilitarian score. Since the block is composed of partial blocks, and each partial block has a proposer who's a winner, basically, and there's a loser as well, for as we can earlier seen. And there's a commit. Those who had committed basically fall into this positive score, and those who had not committed basically in the loser score. And heartbeat messages, if broadcasted, yes; if broadcasted, no, for negative sense. And malicious is basically to capture all the malicious actions. For example, the signature forging or delaying the block proposition, or failing to commit the message. And then we calculate the effective utilitarian, which is positive minus negative, calculated by fairness. Fairness is basically to give a boost to the participants who are least scorers, and give a boost to the participants who are the highest scorers, and lesser credential to the least scorers. Basically, the idea is like ideals will get 0, the weak ones will get better coefficient. So, and then based on the score, what we do for an epoch, if there's a new epoch, we propose a new quorum. We calculate the score, we sort the score, and then we classify them as ideal, which is the best, utilitarian, fair, and weak. And then we form a new quorum based on this classification. And if it's a very low score, we suspend it for a configured number of epochs. So let us look at the results. Basically, the first result, what we have is based on the just to understand the QBA behavior, we have the various networks types. Basically, we tested QBA on lattice, mesh, and Schwarz-Strogatz, and the quorum is 5. So what we can see from here is basically the lattice, the mesh is the best performing, but it suffers from a wiring connectivity problem. Like the wiring connectivity cost is higher. A lattice is acceptable, but what Strogatz, it's like for large network size, it's basically a derivative of lattice, but it's completely randomized for small world phenomenon. So it's good for large networks too. So we choose mesh as our for our testing. And then we proceed to see the number of quorum member limit influence, because our consensus algorithm is revolving around quorum. We test it across different quorum size. Basically, it decides the number of quorum participants as well. For example, when we consider quorum as 5, and then for a case of 20 nodes, it will have 4 participants in each node. So what we can see here is like quorum 4 and 5 have the optimum for 20 and 25 nodes, because the idea is basically when we reduce the quorum size, we can get better performance, like quorum member participation. But we suffer from liveness problems, because when we have lesser participants, in case of failures, the nodes can drop, and then we cannot complete the consensus intra-quorum consensus phase. So next we test like holistic manner on the QBA protocol. For example, we see a normal benign behavior. We test the transaction speed, like increases up to 60 seconds, and then it tries to drop. So what we notice here is basically it's a benign network with no external influence. What we notice from the score is basically the partial block win is quite low for node 3, and the partial block loss is quite high for node 3 and as well as node 8 as well. So what we have noticed is basically in the logs to be correlated, there was a socket communication problem for which the nodes failed in a benign manner. It was not external influence. So we notice a reflection in the score as well. Further reflection can be obtained in the missed commit, because it failed to send the commit messages in the required block propositions. And total score was the least for node 3 and node 8. This is non-cumulative for each epochs. So this is the overall score perspective. And based on the classification, which evolves for each epochs, we see that node 3 and node 8 evolves, but it almost stays in the weak phase. But we see on the node 0, it is mounting to utilitarian phase. So these nodes have continuously failed in the network. So it is prone to suspension. Next, we also test some malicious behaviors. The malicious behavior is basically like proposing malicious partial block and malicious full blocks. This is in the level of intra-quorum, and this is in the level of inter-quorum phase. So when we compare both the results, like we get a more lesser transactions per second compared to a full block behavior, malicious full block. Basically, how do we do is we create malicious in the case like we forge the signature. When on the hash, we just send a malicious hash. Malicious hash performed on a which is signed. So the malicious partial block is proposed by 3 nodes. And also the latency, what they introduce in the system is 200 milliseconds continuously for each broadcast. And here they create malicious full blocks accompanied by a latency of 200 milliseconds. The one thing what we'd like to notice here is like the malicious partial block has a much more bad influence on the network performance compared to full block, because the full block, there is a block fulfiller in case a malicious full block is proposed. And then there's a block fulfiller which takes fulfills that particular block proposition at that phase as a fallback. So it's much less penalizing compared to the malicious partial block. So we also tested some other perspectives from Berserk behavior, like the blocks had certain intervals, they are in the good sense. For example, 50 to 100, they're good. And then they start to behave maliciously. And yeah, it's a kind of randomized behavior. And also we tested some benign, simple case of introducing just latency among the 3 nodes of 100 milliseconds, because when we introduce latency, they fail to participate inside the consensus process. Looking at the results, we can compare that compared to other, we try to compare with click because others are much lesser than Cuba. Like Cuba and Cuba implicit, the difference is basically we reduce the phases inside the intra-quorum phase. Basically, we try to just do the proposal phase and we try to remove the commit and finalize phase, but it is less, it has lesser liveness compared to Cuba. When we compare Cuba, and it performs almost equal to click, but the problem with click is supposed to have a lot of, it is prone to have a lot of forks, and also it's supposed to have certain liveness problem and network stalling, which is solved in the Cuba proposition. So Cuba and implicit is also quite reliable. With reduced phases, it is still reliable, but it is less. It has lesser liveness compared to Cuba. So next, looking at from a CAP theorem evaluation, what we can achieve is like basically in CAP theorem, you can have either of the 2 properties, but it is not the case. Like it should be as proposed by Eric Brewer again. So you can have acceptable level of availability, like you can sustain until the majority of the nodes, honest nodes. And also you can have eventual consistency. For example, in case of anomaly behavior, like proposal of malicious partial block or full block, we can have some fulfillment based on a global timeout that we set. And partition tolerance, like the forks are avoided preemptively because we evolve the network based on its node behavior at each point of time. So this basically avoids the forks in case the network, in case a node behaves maliciously or has failed benignly. From a blockchain trilemma evaluation, that is, it is quite hard for a blockchain to achieve all this scalability, decentralization, and security. We achieve a respectable consortium level scalability among the nodes because we've reduced the communication complexity by pipelining, parallelizing, and also changing of the data structure. Second one, utilitarian fair decentralization, like we give importance to the score, and also we give importance to the weak scorers so they can improve their score. So they have a fair decentralized perspective here. And adaptive security, like in case of malicious behavior, it is reflected in utilitarian score, which evolves the network again based on being resilient to the incoming attacks or security failures. So we can conclude that Cuba fulfills the performance closer to click, but at the same time, it also guarantees the finalization, the liveness problem, as well as the fairness and acceptable scalability, even in benign or non-benign conditions, which suits the mobility use cases. We would like to conclude, like we have started with the mobility data certificate data monetization service, and then I further tested these consensus like PBFT, EBFT, click, and Aura, and find in Grandpa. And then we and then I homogenized the study to make sure that all the problems that we uncovered is true. And then I proposed the Cuba protocol to overcome the scalability, liveness, and consistency issues. And then I evaluated the cloud performance and evaluated the Cuba protocol in cloud implementation. The perspectives is basically like the one is privacy, because privacy can be addressed at 2 levels, both at the use case level and both at the consensus level. Privacy preserving is quite different from privacy by design. So privacy preserving, like we have not explored these aspects, which we would like to explore both in the consensus level and both at use case level. And layered solutions, like since we concentrated on layer 0, it is a good point. We can build multiple layers on top of it, which can create faster throughputs, and then it can be stored in the layer 0 protocol. And sharding, we can divide the entire chain into multiple parallelized chains, which can process individually, and then use Cuba as a consensus protocol, which is something we would like to explore as well. And open source adoption, it should be more verified in order to be adaptable to the open source enterprise and consortium perspectives. These are some of my developments which I've released on the public GitHub for the use cases of certification, and for the use case of data monetization and the blockchain simulator, and only for Cuba, along with Cuba implicit as well. And the results are collated here. Some of our publications as part of this work. Yeah. And one thing we noticed, all the issues that we uncovered in Ethereum was reported responsibly to the open source community, which is acknowledged back by them. Yeah. Thank you very much. Thank you.
So if I'm correct, this will be Cyril Bertel, sorry, who's a professor in Normandie University. Can you hear us? We cannot hear you yet.
Désolé, j'avais oublié de remettre mon micro.
Okay.
Donc, si ça ne dérange pas, je veux bien intervenir en français. Si on est
oui, monsieur. Oui.
OK. Donc, d'abord, je vous remercie pour cette invitation à cette soutenance de thèse. Donc, le sujet est vraiment, de mon point de vue, très intéressant. Je suis moi-même pas mal impliqué dans des projets partenariaux via des labs comme des CIFRE, notamment avec des acteurs portuaires au Havre, hein, puisque c'est une activité importante, et sur la mobilisation justement de blockchain. Donc c'est vraiment, enfin ce travail est vraiment un très beau contexte collaboratif hein, avec le secteur de l'industrie automobile, avec Renault notamment, et qui amène à une contribution, me semble-t-il, qui est vraiment significative pour produire des innovations à un fort potentiel sociétal, hein, puisque l'automobile est quand même un objet très utilisé aujourd'hui. Alors, je remercie le doctorant pour sa présentation qui apporte des améliorations importantes par rapport à quelques petites lacunes qu'il pouvait y avoir dans le document. Donc, ce que j'ai beaucoup apprécié, c'est le démarrage de votre présentation. Je trouvais justement que dans votre document, donc, vous démarrez assez rapidement en mettant le doigt sur une question qui est vraiment essentielle dans le fonctionnement des blockchains, qui est la gestion des consensus. Hein. Et c'est aujourd'hui, si on entend beaucoup parler de blockchain, beaucoup d'outils, beaucoup de preuves de concept, en fait, la mise en production est souvent encore assez discrète ou pas toujours, enfin, on ne va pas jusqu'à la limite, jusqu'à la mise en production, parce que justement, on a des limitations de passage à l'échelle qui sont liées justement à cette gestion de consensus. Donc, c'est effectivement voilà, un élément important. On connaît les limitations des preuves de travail qu'on a dans les bitcoins avec les catastrophes énergétiques que pourraient générer ce genre de blockchain si elles étaient répandues à une large échelle. Voilà, donc effectivement, vous placez bien dans ce contexte-là et dans votre document, vous démarrez directement sur des questions sur ces questions de consensus. Mais justement, ce qui me manquait, ce que vous avez ajouté dans votre présentation, c'était un peu d'expliquer où le consensus intervenait dans le mécanisme des blockchains, sur le chaînage de blocs, sur le support de réseau peer-to-peer, sur rappeler un peu la gestion avec les smart contracts. Et je vous remercie beaucoup d'avoir ajouté ça dans votre présentation. Et je vous encourage d'ailleurs dans votre document, si vous avez le temps, de l'enrichir un petit peu par ce contexte-là, de façon à ce qu'il soit plus abordable à un public assez large, puisqu'une thèse ne s'adresse pas forcément toujours aux spécialistes pointus sur les sujets traités. Voilà, alors, par exemple, dans votre document, vous partez assez rapidement sur des taxonomies de distributed ledger technology qui sont parfois difficiles à bien comprendre si on n'a pas précisé les concepts. Alors, j'ai vu aussi par rapport, si j'ai bien compris comment vous avez évolué dans la présentation, moi j'avais justement dans votre document, hein, puisque comme j'ai fait le rapport, j'ai essayé de faire le rapprochement entre le document et votre présentation. Euh, Même si aujourd'hui on s'intéresse plus à l'évaluation de votre présentation. Mais vous aviez dans votre document un schéma en début, alors en page 4, dans lequel vous sembliez différencier les distributed ledger technology et en dessous vous aviez des schémas des blocs dans lesquels apparaît blockchain ou pas. Qui sont quand même souvent présentés comme étant deux intitulés pour une même technologie. Je vois que dans votre présentation, vous avez fait évoluer ces schémas-là. Donc, est-ce que pour vous, il y a une différence? Première question qui m'interrogeait d'ailleurs, hein, parce que vous êtes un spécialiste de toutes ces technologies et vous montrez dans votre document que vous êtes allé chercher vraiment des choses à la pointe aujourd'hui. Est-ce que finalement, pour vous, il y a une différence entre la notion de distributed ledger technology et la notion de blockchain? J'ai l'impression que cette différence est un peu estompée dans votre présentation aujourd'hui et elle l'était moins dans votre document.
Ok. Ah oui, c'est une très bonne question, monsieur. Oui, je vais répondre un peu euh, en anglais, s'il vous plaît.
Oui, oui,
Euh,
oui, pas de souci, oui.
um, we I can see. I mean, the distributed ledger technology is more like an like which encompasses other technologies, or because there is a more common understanding at the initial process of transaction initiation, the validation, verification, and the agreement by the nodes. And then only in terms of the structure, the final structure where it is stored, there is a difference. But because even in some kind of DAGs, they try to implement the blockchain technology. Initially, they started with the different type of consensus algorithm, but right now they're moving more towards the blockchain consensus algorithms, mix of both. So I can see there is a kind of difference between all these aspects, because in hash graph we have a set of vertices which are connected with other vertices, and they perform a kind of virtual voting, which is kind of different from the usual DAG sense. Like there's a gossiping mechanism, which is quite different. So I see there is kind of a little distinction between all these technologies. So that is why I wanted to mention the importance of knowing the scale and the scale of each technology, because the blockchain, the fundamental problem was throughput, and because of the problem of throughput, they proposed there was a proposition around the DAG structures in order to accommodate finalize the transactions instantaneously. But although they have not fulfilled the promise, they are trying to improvise the promise on that thing. And Hashgraph, it's another aspect, like more on private consortium blockchains, because Hashgraph is much more closed with private participants. So there is a kind of difference as well in terms of constraints as well, which presents for each blockchain. And moreover, earlier the IOTA DAG, for example, in terms of DAG, they were initially public with no proof of stake. Right now, they enforce proof of stake in the algorithm. So I see there's a pretty lot difference between them. And moreover, the transaction finalization is different in case of DAGs. For example, in DAGs, when we create a graph, we can create a blotted graph, a graph which can be created by malicious participants, which can change the finalization because the graph because in DAG, the finalization depends on the number of attachment of vertices to the confirmed transactions. So which is much more different compared to a blockchain, which depends on the length of the, as you can see here, even though we create forks, it depends on it depends on a different resolution protocol like grandpa. So the concerns are different, but they're trying to converge a bit, but the concerns and the pathway is quite different.
OK. Merci, je comprends votre point de vue qui est intéressant, justement, qui permet de mettre le doigt sur différentes approches autour de ces mécanismes. Mais par contre, vous voyez, vous mettez en avant, par exemple, le fait qu'on ait des technologies, enfin des blockchains publiques ou privées. Donc, vous voyez, c'est un peu tout ça, je pense, qui serait vraiment intéressant, je pense, pour améliorer votre document, de redonner un peu le contexte de toutes ces approches qui sont importantes, en fait, sur les choix qu'on va faire derrière et sur même la manière de présenter les concepts, comme vous venez de le faire. Mais pour que les gens comprennent comment vous distinguez les DLT avec les blockchains, il faut
Oui.
justement que vous ayez introduit un peu ces notions-là. Parce que c'est
OK.
quand même un point de vue, voilà, tout le monde n'aura pas forcément votre point de vue en disant que finalement, ça peut être un peu la même chose. Mais c'est vrai que derrière Distributed Ledger Technology, on va plus se focaliser sur ces aspects de consensus.
OK. Oui, oui, je
Le,
vais
le,
je vais
le nom évoque bien évoque ça, alors que alors, je vais essayer. Alors, moi, je voulais revenir sur les. Vous parlez de services de monétisation.
oui.
Alors, je vois dans les slides, alors je ne voyais pas toujours les numéros de slides, hein, c'est pas facile de. Mais quand vous avez présenté le problème sur les odomètres, je ne sais plus quel slide c'était, je n'ai pas pu noter le numéro parce que comme il y avait la vidéo, c'est au tout début, là, quand vous présentez un peu les cas d'usage pour l'industrie
Oui,
automobile.
oui, je vais revenir sur le slide.
Alors, vous parlez, dans ces slides-là, vous parlez de cette monétisation de la donnée.
Ici,
D'accord. En plus, il y a de toute manière un coût des transactions. Oui, la slide qui est juste avant, en fait.
ah,
La 16, c'est juste avant. Là, vous avez en haut, justement, un Inner Token Economy. Donc, qu'est-ce que vous voulez dire par là et comment, je n'ai pas forcément bien compris, hein, peut-être quelque chose m'a échappé, sur justement comment on va gérer ces frais. Il y a des frais de transaction à prendre en compte. Et comment votre monétisation de la donnée, en fait, elle intervient dans les cas d'usage que vous montrez? Ou est-ce qu'elle intervient, ou peut-être qu'elle n'intervient pas dans les cas d'usage, mais j'ai plus de mal à comprendre comment, en fait, on mettait en avant la monétisation de la donnée dans, par exemple, les problèmes sur les odomètres.
ah oui, oui, OK. Oh oui, OK. Je vais vous répondre, monsieur.
Ouais.
OK. Here, what we try to solve, it's not, it is more like we try to certify the data just to have an assurance on the data which is transferred. Like, for example, to assure that the vehicle has completed certain odometer kilometers for certain journey. And what we try to do here is basically like we create, as you have mentioned rightly, it is more like it's not a public blockchain. It is more like a private blockchain. It is not more like, it is a private blockchain, a consortium, private consortium blockchain composed of several participants, as we assume here. For example, OEM, the government, and the assurance partners, which can host the nodes. Basically, it's secluded from the public. What we try to do here is basically once when the vehicle issues an API request to the blockchain, that is the consortium, private consortium blockchain, what it tries to do, like there are admins, which are designated admins, for example, designated admins who validate the transaction. And then in case of validation of the transaction, they look for the incremental notion, that is the incremental notion of the odometer kilometers. And once it is done, they deposit the tokens inside the wallet's vehicle. So that is why I call it economy. Like we deposit the token, we create it. Actually, the admins can only create the NFT tokens, which represents the odometer kilometers. And then they can transfer it to the vehicles. So it is a one-time transfer, which cannot be retracted back, because it's basically an NFT once deposited, it is not retracted back. So that is why we call it we call it as a smart inter-token economy smart contract orchestrated concept. Basically, that this consensus which I talk about is inside a smart contract. Basically, the admin has to give a validation on the transaction which is ejected by the vehicle. And obviously, we have another level of consensus which happens inside the click, obviously, the click or PBFT or QBFT. That is a consensus at the level of the transactions. So that is why there is a misconception around the two types of consensus. Like here, the admin should agree basically on the, for example, a vehicle transfers journey, and after a journey, if it emits a transaction, the admin should collectively agree on that is 2/3, and then it should validate the transaction for the deposition of tokens. So that is why you call it as consensus here. So it has nothing to do with the original layer 0 blockchain consensus transaction. It rests the same. It is click, PBFT, EBFT. Yeah, actually, this was a point because due to the brevity of time, I did not explain. Sorry, but yeah, this is the concept actually, actual concept.
Ok, là on est plus sur des tokens, effectivement.
Exactement, c'est ça.
Ok. Alors, après, j'avais juste une question un peu sur vos aspects de développement. Dans la slide 22, vous parlez de développement en Java. Est-ce que vous avez finalement, vous développez des smart contracts, donc vous avez fait du développement à partir des bases d'Ethereum. Enfin, je ne sais pas, vous avez reconstruit un système de blockchain privé dans votre simulateur, c'est ça? Mais en vous appuyant sur les concepts, enfin, ou les bibliothèques d'Ethereum, ou vous avez redéveloppé par vous-même, en fait, les constructions des blockchains?
Oui, c'est une chose, oui, on a mis dans la perspective, mais oui, vous avez très bien remarqué. Comment on a construit le simulateur, c'est à partir de Java. On a créé un network module en utilisant le socket communication pour créer un network module. Et après, on a créé le data structure module pour chacun, par exemple, le blockchain, the blocks et les transactions, le payload. Et comment on gère, on stocke dans une pool pour chaque, soit si c'est une transaction message, on stocke dans une transaction pool. Si c'est une consensus message, on stocke dans une transaction pool. C'est vraiment un queue, vraiment, un synchronized queue. Après, à partir de là, ce qu'on fait, on crée un consensus module qui écoute toutes les consensus messages et qui stocke toutes les messages. Et par rapport au consensus algorithme, ce qu'on crée, par exemple, PBFT, EBFT ou QBFT, on change la notion de protocole et ça reste la même chose. Par exemple, pour le network, pour la data structure, pour les autres de crypto, pour le API, ça reste la même chose. On change juste le consensus module pour chaque dérivative. Et oui, c'est pas vraiment une question de privé ou public, c'est vraiment une simulation. Oui, c'est une travaux qu'on doit faire comme la prochaine étape. Mais simulation, c'est pour être un peu précis, le database, on n'a pas utilisé un database, c'est toujours runtime memory, c'est toujours le JVM memory qu'on utilise, c'est vraiment. Et après, pour la partie de transaction payload, c'est vraiment un message transaction. Et message transaction, ça va être CMT, c'est pas un smart contract transaction, parce que le smart contract transaction vrai, c'est une transaction, c'est créé à partir de l'API et encodé dans une transaction. Après, c'est décodé, c'est exécuté dans l'EVM machine. Et après, si c'est valide, c'est stocké dans une state séparément pas dans le même DB, c'est une DB séparée. Et c'est comme ça, ils ont fait une chose compliquée pour maintenir le smart contract state. Oui, c'est séparé avec le blockchain state. Mais nous, on n'a pas focalisé sur ça. On a resté surtout sur le consensus et le transaction message.
Ok.
Transaction message et consensus message. Et aussi, un autre problème, account maintenance, on n'a pas concentré parce que normalement, account maintenance, c'est balance de crypto-money transaction ou bien c'est par UTXO. Par exemple, l'UTXO, ça veut dire on crée une crypto-money, on divise en plusieurs, par exemple, pour 1500 crypto-money, on crée une UTXO, après on divise une UTXO en 2 parties ou 3 parties. C'est comme ça, on diffuse dans le réseau. On ne fait pas toute la complexité là-bas. Encoding et decoding même, on n'a pas fait, on n'a pas fait ça. C'est vraiment encoding et decoding. Pour l'Ethereum, c'est recursive link prefixing. On n'a pas fait ça. Encryption, decryption, on est resté simple pour concentrer sur le consensus. Nous, on a fait, oui.
Oui, ok,
Oui.
je comprends bien. Mais alors, du coup, finalement, quand vous voudrez mettre en production, je sais pas, pour Renault, par exemple, ces consensus, vous allez vous rattacher à quoi? À une blockchain de type Ethereum, Hyperledger ou des choses publiques ou
Oui,
privées?
oui. Ok. Oui, c'est une bonne question. Ce oui, c'est une vraiment bonne question. Après le résultat j'ai eu avec la réalisation de réalisation de la mobility use case, la data monétisation et certification, ce qu'on a décidé, soit on prend en simulation, ou soit on prend une vraie blockchain. Mais si on prend une vraie blockchain, c'est pas faisable dans le temps duré de thèse. C'est pour ça qu'on a resté sur la simulation. Et parce que on doit participer vraiment dans le open source community pour comprendre bien la logique et ça va prendre le temps. Et c'est pour ça qu'on a décidé pour aller vers la simulation. Mais la future étape, c'est pour bien, on a déjà contacté un blockchain développement, c'est Ethereum, c'est un type de Ethereum blockchain, je ne sais pas plus exactement le nom. Juste pour infuser, pour essayer pendant la thèse, c'est avant 2 ans, pendant la thèse. Et après, c'est pas faisable oui, c'est pour ça qu'on a décidé tourner vers simulation. Maintenant, le substrate, ça permet d'infuser notre consensus, n'importe quel consensus. Ça doit être un chemin, ce qu'on prend pour réaliser le blockchain dessus. Ouais. Après, je ne rappelle plus le nom exactement, ce que j'ai contacté, c'est assez connu. C'est dans le Ethereum.
Ok. Est-ce que j'ai encore le temps pour une dernière question pour pas trop monopoliser Je- J'avais juste quand même un point qui m'intéresse bien par rapport à l'activité. Vous parlez dans Cuba donc de la mise en place de Swarm Process, hein, ce qui est
Oui,
donc avec la mise en place de Quorum.
oui, c'est ça.
Si
Oui,
je comprends bien, parce que vous faites une évaluation après globale de Cuba, mais après, ce qui est intéressant, c'est de comprendre dans ce que vous avez implémenté dans Cuba, qu'est-ce qui est vraiment apporte un impact important dans votre résultat. Donc, si je comprends bien, c'est ça, je voudrais avoir une confirmation de votre part, c'est bien cette répartition et gestion de quorum qui permettent de diviser en fait la gestion du consensus, qui vont vraiment apporter un impact important en termes de scalabilité. Euh, Est-ce que c'est bien le cas? Est-ce que je comprends bien
euh,
que c'est bien cette organisation qui est originale d'ailleurs de, de travailler, d'utiliser des quorums pour répartir en fait le mécanisme de gestion de consensus, puis après agréger des résultats qui est impactant sur l'amélioration du passage à l'échelle.
oui, oui. J'ai mis un slide pour le.
Et alors, du coup, j'ai une deuxième question. C'est quand vous parlez de SWAM hein, dans les méthodes d'intelligence collective, ça évoque de l'auto-organisation, ça évoque de l'émergence. Alors, j'ai pas bien compris. Alors, peut-être que vous parlez il y a beaucoup d'aspects hein, dans vos travaux. Euh, Est-ce que les quorums, si j'ai bien suivi, les quorums en fait se réorganisent ou pas? Est-ce que vos nœuds, les nœuds qui sont à l'intérieur du quorum, est-ce que les quorums vont se réorganiser ou vont se redistribuer différemment au cours des processus dans les quorums?
Oui, oui, oui.
Oui,
OK. Je vous réponds. Par exemple, si on considère un cas de malicious Berserk chain, le
oui,
malicious Berserk chain, c'est normal pour 0 à 50 blocs. Après, ça tourne un peu malicious, ça tourne un peu normal encore. Après, ça tourne, c'est comme un sine wave. Le Berserk, c'est behavior, c'est comme ça.
oui,
Et on voit le graphe aussi, mais c'est normalement le behavior, c'est total, c'est pas cause de temps, c'est cause de block heights, normalement.
hmm,
Et si on voit, il y a une évolution il y a une évolution, par exemple, le node 7, 8 et 9, qui fait le malicious actions. Ce qu'ils font, il fait un full block proposition, c'est malicieux, et après, il introduit l'attente aussi dans le réseau. C'est pour ça, son missed partial blocks, ils ont raté pour donner le vote pendant le partial blocks. Et
ok,
aussi, le missed commit, c'est évolue un peu par rapport au score. C'est à cause de différentes époques, c'est évolution, c'est cela. Et
hmm,
malicious aussi, on a noté pendant l'époque. C'est comme ça évolue normalement le score. C'est par rapport au score, on calcule l'effective utilitarian. À partir de effective non-cumulative utilitarian, on fait la classification. Normalement, oui. Normalement, le node 7, 8, c'est normalement, ils ont déjà dans le week offert utilitarian une suspension. Ça veut dire qu'il va être suspended si ça continue pour successive epochs.
hmm,
C'est comme ça l'évolution. C'est normalement, ils sont dans le rang très bas par rapport aux autres. C'est comme
ok.
ça on voit l'évolution. Et après, j'ai préparé un slide pour la partie de Swarm aussi. Et je sais pas si où ça. Donc, c'est intéressant. Exactement, j'ai pris le chemin de Swarm, mais je voudrais préciser un peu.
Non, mais
Oui,
j'ai.
exactement, c'est ça.
Oui, c'est
Par-
ça, c'est
oui,
les méthodes
OK.
d'auto-organisation en fait, qu'on
Oui,
connaît.
c'est ça. Par
Hmm.
exemple, oui, j'ai pris l'exemple de
Moi,
Ant.
je comprends l'intérêt, notamment pour détecter
Oui.
des
Et après, l'autre chose aussi, ce qu'on a mis pour être le Sisyphus coefficient, c'est-à-dire pour le swarm, normalement, il y a un phéromène qui a un decay coefficient aussi.
Hmm.
Oui,
Ouais,
oui, c'est ça. C'est exactement ce qu'on a introduit dans le protocole aussi pour le Sisyphus coefficient. Ce qu'on voulait dire, c'est on va prendre le score qui est récent par rapport à l'ancien bloc. C'est ça, c'est ce que I was inspired by this same protocol
hmm.
to fuse it in Cuba. Exactement. C'est pour ça on évolue le network aussi parce que le score, on compte le récent score. Oui.
Et ça, je pense que c'est une contribution vraiment intéressante de montrer comment vous pouvez adapter ces mécanismes de comportement des sains adaptatifs sur ces technologies de blockchain. Bon, bah, je vous remercie pour vos réponses à toutes ces questions. Et,
Merci beaucoup, monsieur. Oui,
je laisse la parole à mes autres collègues.
ok. Je vais noter votre tour. Merci.
Merci beaucoup. Du coup, je propose qu'on passe à la deuxième rapporteuse, Madame Timai Trong Nguyen, qui est à distance également.
Merci, Monsieur le Président. Euh, donc,
Merci.
tout d'abord, je voudrais rejoindre mon collègue pour remercier la présentation et aussi le manuscrit sur les contributions qui sont très intéressantes. J'ai quand même quelques questions. Donc, je vais commencer peut-être par le point que mon collègue est en train de poser la question, qu'on est là. Donc, je m'intéresse effectivement aux notions de quorum dans le protocole ou de consensus proposé par le candidat, c'est-à-dire justement dans l'algorithme Cuba. Donc, ma première question, c'est comment déterminer que le score est similaire? How can you determine that the score are similar or not similar?
Similar in what sense, madam? If I would like to just rephrase the question.
Okay. That protocol, you say that you will group the nodes into quorum, right? And the way to group the nodes is based on a score. That means the effective utilitarian score. And I understand, and you correct me.
Yeah, no, you are correct. Okay, I can understand your question now. Thank you for the precision. Like basically what we try to do, you can show on the slide. I can just explain a bit more about the utilitarian phase, if I can get your time. Actually, it's much more detailed. Actually, like once we complete the score for a block, we then agglomerate for a particular epoch. So, and then we apply the fairness quotient, and then we apply the Sisyphus to take the principle of like for each epoch we have a score, and we give more importance to the recent epochs. And then we basically it's like forgetting coefficient is calculated based on this formula, exactly the same formula, where we compare with the current epoch and the previous epochs, and then we apply we then add apply the forgetting coefficient for each previous epochs, and then we calculate the total score for all the nodes, and all the nodes then we get then we sort them, and then we are required to produce certain number of quorums, which we decide at the start of the network. So when we decide the start of the network, we divide them into intervals. Like for example, the first best interval will be comprised of the ideal utilitarian, and the second interval mostly in the case it will be like utilitarian, fair utilitarian, and weak utilitarian. It's not a perfect division based. It is not a perfect division, but it's a division based on the scores. We sort them, and we, as I mentioned in the as we mentioned in the report as well, like we organize them based on we organize them into intervals, and also how to say, it can be a mix of, for example, if we sort them and we organize them into different quorums, it can be a mix of, for example, fair and weak as well. So leaving alone the suspended nodes. So it's not it's a classification just to the classification. Why we do the classification is best to render a kind of fairness to the nodes. For example, if they are weak, we give more importance to them in terms of score. The basic notion of classification is that. And then the sorting of quorums is basically based on the sorting of the score of the nodes. So the classification is not to agglomerate all the ideals into one, all the fair utilitarian into one. It's basically more like it depends on the interval actually. For example, if you have 10 nodes, and then if 2 nodes are suspended, then we are left with 8 nodes, and we have to satisfy certain quorums. So based on that, we organize. So it's kind of interval, actually, in the kind of implementation, it's kind of interval calculation based on the number of quorums. It's not perfect classification that we try to do here. For example, it's not exactly, that's why I mentioned it's similar, but not exactly the same utilitarian scores of nodes.
Okay, thank you. So yeah, okay. So the number of quorum depends on the number of intervals of the score that you decide in your algorithm. But so do you take into account the size of your of the network? That means the number of nodes, or
Okay.
you take into account the network topology or something else in order to decide the number of quorum?
Okay, yeah, that's a good question, actually. Due to the brevity of time, I was not able to explain it much clearer. But actually, in my second result, the first result, I presented network topology. The network topology was just to experiment with different types of topology, how it behaves. It is nothing to have with the quorum organization. Because the ideal case is mesh network, which does not happen in the real networks. Because as I told earlier, we wanted to concentrate on consensus process. Just let me go back to the slides. Yeah. At this, what we try to understand is basically Cuba, how does it behave in various network topologies? That was the initial motive. And it was not the best choice. Mesh is obviously not the best choice. But during our test, we had continuously used mesh, because mesh has higher wiring connectivity problem, because all the nodes form a complete graph. In this case, there is a high load of socket communication. So this, but it's much faster. For example, here we have a lesser number of nodes. And the communications are lesser. Lattice is more like connecting with the nearest neighbors, which forms a kind of grid. And what Strogatz is more like an ideal case. For example, when we take like a big public blockchain network, for example, in France and connecting with Germany, it's most like distant nodes. Here we take the case of lattice, which is the lattice connection normally is reorganized into a small world network or Watt-Strogatz network in order to connect a distant node. Like it is the best mode actually for long distance connection, like the Watt-Strogatz model. We wanted to just experiment this phase. But to be real, in case of real blockchain developments, what happens in reality, it follows the real routing. It calculates the distance between its peers. Normally, it's based on a boot node, and a blockchain node connects to a boot node in order to know the peers in the nearest to it. For example, not nearest, like lesser latency. And then it connects to the nearest peers, and then it drops and then connects it back based on the nearest peers. It's basically a routing problem in calculating the shortest distance available in, for example, libp2b libraries or devp2b libraries used in Ethereum. We have not replicated in that sense. So that is a point I would like to precise here. The second point I would like to precise here is the decision of the number of quorums. Decision of the number of quorums, basically, the quorum has a major impact on one intra-quorum phase, because as we can see in earlier, it is a communication complexity quadratic. So compared to other phases, which more are like single phases. So the communication, I have added another slide on algorithm complexity as well. So what we try to do here is, like, if we try to minimize the number of members inside the quorum, yes, it's a good thing, but it reduces the communication complexity. But the problem is, for example, there is a liveness issue. So we try to balance the both. We try to have an optimal number of quorum participants and also guaranteeing liveness, for example, to accommodate certain failures. For example, if we have a partial block proposer who has failed at a certain point of time, obviously it can be picked up by another partial Buck proposer. So that is the point that we try to test in this case. We try to test with multiple, starting with 2 quorums, for example, for 5 nodes, for 10 nodes, for 15 nodes. Example, 2 quorums in this case, like for example, for 10 nodes, it will be 5 members. What we notice is basically to have 5 as the best quorum limit 5 as the quorum limit. For example, as we can see here, in 20 and 25 nodes, which is the max we have tested, for example, a quorum 4 performs the quorum 4 performs the better, and for 25 nodes, the quorum 5 performs the better. 5 quorums, so divided by 25, it's actually 5 members per each quorum. So that is why we wanted to precise here. It's just a data that you would like to precise here. The epoch limit is basically like 25 blobs. The number of quorum inside a quorum increases the failure tolerance or liveness. That is the point we try to precise here. So it's nothing to do with epoch limit, or it's nothing to do with topology.
Thank you. I think that it's interesting to see that finally there is some trade-off. Some trade-off
exactly
between the number of quorum and the size of quorum, because we'll have some impact on performance on the 2 phase, the intra-quorum consensus and the inter-quorum consensus. So do you think that is it possible to for the modeling, that means can you model the problem of optimize number of quorum as an optimization problem and identify on the parameters that we can vary in order to find the optimum number of quorum?
Yes, yes, it's definitely a combinatorial optimization problem. Yes.
Okay.
Yes, the number of quorums, it depends, like the factors, like it's but I've used solvers, but not in my thesis, but during my master studies. Actually, it depends, like it depends on multiple factors, like for example, the liveness. If you have to quantify certain factors in order to optimize the problem, it will be liveness, for example, in order to avoid the forks and the network stalling, and also the failure tolerance as well, in case of if we consider certain amount of failures to happen. Yes, those are kind of quantified factors that we need to take into account in order to arrive at an optimized value. But here, what we do is, yes, that is certainly a factor. And also we need to take into account the utilitarian score. The future proposition is basically, as you actually mentioned, as mentioned in my report as well, to form quorums based on the to form quorums based on the utilitarian score. For example, here we perform just a sorting and just we classify and then we sort it based on the intervals. Maybe the ideal way is to pick up ideal utilitarian and put it in the quorum, and to depending on the quorum, to have a balance between various types of utilitarians, just to mix them up in order to ensure that the liveness is maintained in the network. This is one kind of aspect also that we have mentioned as future perspectives, to introduce utilitarian weightage assignation, both through the quorum proposition as well as the transaction emission and the consensus message transmission as well. Because the transmission which happens by high utilitarian scorers, like ideal utilitarians, can be assigned more weightage because they are very ideal, honest nodes, which can improve the throughput in the network. So yes, as you mentioned earlier, yes, this is certainly a optimization problem that we take into account. Yeah.
Thank you. Yeah, exactly. You mentioned the problem of honest and malicious nodes. Um, uh, okay. I'm from networking. I'm a specialist in networking, not in this system. And I still have a question. This is a question that I have for a long time.
Okay.
Not only for you, but this is, I think that in distributed system or in blockchain in general, you consider there is a strong relationship between malicious nodes or behavior and the delay. Because it seemed to me that you consider that if there is a node introduce an important delay, you say that this is malicious. Is it?
Uh,
Or-
yes, madam. Yeah, yeah. Interesting to know that. Yeah, I think blockchain also has a lot of influence over the network. I mean, networking layer. Yes. The point, like, here, what I simulated is basically the first scenario is basically I introduce benign latency. I call it benign latency because it can introduce a latency benignly, not not in the terms of malicious actions. What I try to do in terms of malicious actions, like when I propose malicious partial block or malicious full block or berserk behavior, I try to make it more hard actually. Just to introduce, along with the proposition of malicious partial block, I try to delay the consensus as well. So that's why I introduce latency. So when I call it malicious, to be clearer in the implementation of the consensus, latency proposition is not malicious. What I consider latency proposition indirectly, no, not indirectly, directly influences the transmission message and reception. So directly influences the various phases of the protocol. So when how does it influence? Basically, when I expect a vote to be sent by a node member inside the quorum, if the vote does not receive, okay, if I receive the threshold, okay, fine. I have not received the vote from a latent node. What I do, I progress with the consensus, like because I achieved the threshold. And what I later do at the end of the consensus phase, I calculate the utilitarian score, which is broadcasted, which is calculated by each node on the reception of a full block. So during that time, I can easily count the number of votes received based on its signature, and then I can decipher that this the particular node did not submit its vote. So that is how I calculate the missed commits actually. And also for a particular block proposition, in case he missed to propose a partial block due to latency, I penalize them. But the penalization is not high because the scores actually, I have a slide actually where I can show the scores. The penalization is not high in case of latency, but in malicious, it's certainly penalizing, because malicious, I decipher direct and store it in a different storage. And then during the, because malicious actions are not part of the blockchain full block, or because I cannot decipher, I cannot understand the malicious action. Like when, for example, when I have a forged partial block, what the node does, it stores in a different storage. It checks the signature. If the signature does not match, it stores in a separate storage. And after it then broadcasts it as a separate message. The malicious message passing is different from the other message, other scores which are calculated. Like the malicious score calculation is based on a different message passing instantaneously. It does not depend on the full block, which needs to be unpacked to see how many votes are there, who proposed a block, who did not propose a block for the particular round. So that is how I make the difference in terms of implementation.
Okay. Yeah. Of delay. Yeah. Sorry.
Yeah. Because why I did was because the malicious action is more graver. Because if a node, just to precise a point, sorry, malicious action is more graver, so it follows a separate message pool and a separate storage, and it diffused instantaneously across the nodes. Yeah, that is the only thing I wanted to precise more.
Yeah, I have a question well related to the problem of delay. Because your work will be applied in vehicular networks, that's mean related to vehicles. And from networking point of view, connection is wireless connection and wireless network are not reliable.
Yes.
It can introduce the delays. The variation of delay is very high. So how you take into account this particularity of vehicular network in your study?
Yeah, I mean, vehicular networks, yes. Normally, the best innovation right now is like we have VANETs or MANETs, so which connect to other vehicles like a peer-to-peer fashion in order to transmit the message. So which can be compared as a kind of blockchain network, we could say, or maybe a peer-to-peer communication. I would say, which also needs a consensus process in order to verify and send the message. So that could be one point of view that we could take into account, because I think any OEM for that matter could not assure a communication 100%. For example, in tunnels or in case of high altitude mountains, I think that could not be the case. But in case of manets, which operates the similar case like a peer-to-peer networks, I think that could be a point of view that we can take into account. But in that case, right now we have, but it's more like it is more like a consensus which is not Byzantine. So it's more like a it's more like a consensus process for atomic transfer so where we agree on a state. So that could be one point of view that we could take for vehicular networks, because yes, certainly the assurance by any OEM, I don't think it is there for vehicular networks. Is it clear? Am I did I reply to your question, madam? Or
Yeah, thank you. Yeah, maybe I will have a last question because there's other member in the community want to ask question. So my last question is about the application. What do you propose? Will be used for, I see that there are two services proposed. The first one is for data certification, for example, the number of users. And the second one is for data monetization. Do you intend to extend your work to other applications or not?
okay, that is a good question actually. Yes, actually the data certification, data monetization was a starting point, and it was a use case that we have chosen because it is more vital. But it is actually it offers more view into the other use cases that can follow. For example, in terms of fairness and the privacy is a more. I think privacy and fairness. Okay, it's okay. I mean, fairness. I don't think anyone cares, but actually, the privacy is more of a grave concern to all the people who participate in this process. So the privacy aspects are more satisfied by the blockchain with the evolution of ZK snarks and other. I think it's more serious in blockchains compared to the centralized systems, because centralized systems right now, the vehicles transmit the data, they collect the data, and then they offer, and then they directly distribute the data to the particular other data aggregators. Like for example, right now we have a lot of centralized systems which operate like Autonomo, Vijo, etc. And also in case of blockchain, there is one solution which I don't remember, which is very prominent, which offers data monetization very seriously. I don't remember. Ocean Protocol. So it works basically on data monetization, which is a decentralized in a decentralized fashion, where you can buy tokens for the data that you want, and then the data tokens rating depends on the truth of the data and the value of the data. So yeah, I think the enterprise, but there are challenges to the development in the enterprise needs, because the problems that we have encountered during this development is basically like there are certain dependencies on the binary development. For example, there are node stalling issues or database corruption. I think if these minor issues are taken into account, I think it should be a good way to take it forward for the real use case implementation, madam.
Thank you. I finished my questions.
Thank you very much.
Okay, thank you very much. So we have a third reviewer, who's Yves Roudier, professor at University of Nice. Please go ahead for the questions.
So I would first like to thank you for your presentation. So I think it's a hard work, a hard job, given the amount of basic knowledge and all the state of the art you have to explain. And I would acknowledge this is also some important part of the manuscript that you've been writing. So sort of organizing all that body of knowledge and making sense of that so that you can introduce your problem and propose your Cuba consensus and related approach. So I think that's something that's important to note. Also that it's rather readable in the manuscript, and I think the presentation also try to remain still at a high level compared with the complexity of the state of the art. Okay, so I think that's something we should note, we should recognize. I think also an important part of your contributions is really trying to make some relatively uniform evaluation of the performance of the distributed algorithms powering the consensuses that you've been presenting, and also your contribution. So I think that's also a laudable effort. And I think Cuba is an interesting proposal also. So you've been doing a lot of state-of-the-art over DLT and consensus algorithms in general. I think maybe you missed a bit. There was a question about the self-organization, and actually self-organization was also something very much addressed in peer-to-peer systems. It's no surprise that, I mean, some of your proposals in Cuba maybe also be related to some proposals that were made in the field of peer-to-peer systems. But it combines other mechanisms as well. So no problem with that. Now I would like to ask a few questions, and my questions are a bit more towards the security spectrum of the topics that you address. Well, first of all, so there was a question from the previous reviewer about the question of delays and the problem to the consensus, and I would also emphasize or raise a question about that problem of what you mentioned as a need to have a reliable channel to implement Cuba. Because I was really wondering about the potential to perform denial of service or distributed denial of service attacks. And in your manuscript, so you consider that this should be devoted to the underlying infrastructure dealing with this kind of issue, and that you build on top of a reliable channel with respect to this problem. And well, I'm not so sure that you can really ignore that at the consensus level. So Okay, what do you think, first of all, about that? Do you have any ideas? Also about the potential impact, because I mean, attacking the consensus means that you would, for instance, be able to freeze the vote at some point, but that means probably being able to locate and attack a large enough number so that it blocks the vote, for instance. So what about that at the intra and inter quorum level? Do you have just any intuition about that?
Actually, first, my excuses. Actually, yes, you have mentioned it right. During my report writing, I focused more on the consensus and certain malicious actions. DDoS, yes, it is really a grave threat. Actually, it is not to be considered at the network level. It is actually, there are different layers of DDoS. I started to explore a bit. I have certain things actually, and I have certain. Yeah. So yeah, DDoS can be at different levels. So that was one of my understanding that I tried to do. So it can be either at the application layer or at the resource layer or at the volumetric layers. So it can target not only at the network layer as I perceive. So like, for example, when I try to understand more about blockchains and the impact on DDoS, like there were, I think even 2023, there was a DDoS attack. Basically, the idea was to flood the network with a lot of transactions, inhibiting the nodes from performing their usual tasks. So, and then in order to resolve this, they did a hard fork, basically reorganizing the network. So it was a very grave attack. So that was missing in my thesis as well. I think I failed to understand the DDoS, so better one. And what we tried to do, what I try to analyze a bit. Actually, in case of private consortium networks, the good point about the thing is, here we are safely focalized on private consortium networks, so that could not be an excuse, sure. But in case of private consortium networks, we can restrict the rate limiting, for example, at the network level, or traffic filtering or load balancing. These are existing techniques not related to the consensus as a sense, but more at the network level. And also there are certain literature, a lot of literature, which takes into account blockchain, which acts as a complement to DDoS attacks. Like, for example, a storage where you can blacklist IPs. But our concern is more like, if we bypass all the firewall, if we bypass all the different layers of security, if a node who can participate, like a consortium participant who can act as maliciously, like sending a lot of transactions, what does it happen in the real case? That was the worst case that I assume, and take it forward. For example, the actor can be like can operate in two ways. For example, like considering for this quorum and this quorum, there is one actor. He only tries to spoil the network by sending a lot of transactions, like only transactions. And consensus message, it doesn't. Consensus message normally, if he does not participate, in the usual consensus process of interquorum and intraquorum, he tries to destroy the face of the consensus just by filling up the transaction pool. Normally, what happens here is like he is normally singled out using the utilitarian score because he do not participate in the consensus mechanism. So that is one case that we can assume. So that is a good case. I mean, that is a good case, but normally the malicious participant is more intelligent. So what he tries to do, he tries to conceal his actions. He sends consensus message regularly. He responds to all the proposers, and he also tries to flood the network. So that is more a harder case. So what happens in this real case is like when an actor sends a message, normally the normal messages are stored in a transaction message pool. That is a different layer. In the implementation, I'm talking about the implementation, not at the protocol level, the implementation level, because I try to take advantage of the implementation. And then at the consensus, only for the consensus message, I have a separate pools for commit, propose, finalize, and full block. Even at this level, for example, at the transaction message diffusion, I have certain, I distribute the transactions to different quorums in a non-duplicated fashion. For example, using hash code checkpoint, I transmit the transactions. A particular quorum receives only a certain set of transactions, which is non-duplicated. So that limits a bit. And what happens here, even if it bypasses all the other all the higher mechanisms, if it bypasses at this level, at the consensus message, it arrives to tries to full the proposed pool, for example, because each has a separate message pool. When the messages are received, actually what we try to do is, like, we only receive a message, each is multi-threaded. So all these are different threads listening to the communication. So when the transaction is received at a network layer, we distribute across different message pools. So we try to take advantage of the mempool structure memory. Actually, we try to have different threads which operate in a multi-threaded fashion, which listens to different messages. So when a particular proposed pool has only, we imagine that, okay, commit pool, proposed pool, finalized pool, all the messages are getting transmitted as malicious sector. There's basically a check actually we do. This actual implementation code, for example, for a proposed message, we take the particular round partial block hash, and also we look in for the message sender, and we add it to the R list only if it has already not sent a message. So basically make a check at this level also. So that is why I made a cross mark here. So this somewhat safeguards the QBA protocol at this level. But certainly what we would like to introduce actually is that we would like to limit the transactions. If it is sent at a faster rate, we would like to add malicious action in terms of DDoS as well, because malicious action we have taken into account right now. So this is one case. Actually, there's a mechanism already there, basic mechanism to safeguard in certain scenarios. The other mechanism that we would like to really extend is, like, take the malicious action as DDoS, like the number of transactions which sends instantaneously at a higher throughput. We try to designate as a malicious action and then report it instantaneously to the nodes to get blacklisted. So that is one thing that actually is a proposition. It also comes under perspective.
In what you're
this one is actually,
you're considering intra quorum attacks.
Yes, no, intra-quorum or inter-quorum.
Inter-quorum as well.
Yeah, both of them, because all of them are message pools different. Because here full block pool is more like inter-quorum, and others are intra-quorum, and this is transaction message pool. And also Heartbeat, we have different message pool, but I did not want to just spread out. But yeah, this is how we do actually.
And do you think the consensus itself might make it possible to
this is what
identify because the compromised actor, because in that case it would be based on a compromised platform.
You're right. This is more that we are taking advantage of the implementation. So yeah, the consensus itself to handle it more cleverly. But what we like to, take advantage of is, like, if as we identified full block malicious and full block partial block, we would like to note the number of transactions for a particular partial block hash or for a particular proposition in terms of votes. We would like to maintain a count, and then if the count exceeds at a huge number of time, like, we would like to transmit as a malicious message. For example, if there's a repeated transaction which is sent. For example, in case of transaction message pools also, we can have a same set of condition. That is one thing. It's more in proposition. It's not currently in place. But that's a good point.
And so ultimately, the compromised actor that performs the denial of service would be removed from the high-ranking quorums based on the utilitarian.
Exactly the point. Exactly the point. But the problem is, like, if he conceals to act as both honest and malicious, that is an interesting point.
Okay. Okay, so I would like to raise a second question, but now moving upwards towards the applications, the use cases of your system. And I would like to start with use case number 2, so which is the monetization of data for the radar application. I was wondering, that's not something you discuss either, if I'm not mistaken. What if bogus data are reported? Because you're talking about monetizing data, having some fair exchange with third-party players in exchange for data transmission. But okay, what if the cars, for instance, are compromised and send bogus data, or even if an intermediate node changes the data somehow? Okay.
Yeah.
The car, the vehicle platform is the most likely source of such an attack.
Exactly. Yes. Yeah. Actually, there are two perspectives to it. Like the two perspective is like, for example, if a guy manages to manipulate the ECU, or in case of recent cars involving like SDV, the central processor, if he tries to manipulate and somehow send manipulated data, that needs to be mostly handled at the cybersecurity level of the vehicle, I think, because if he tries to, I mean, just to differentiate the question, like at the blockchain level, what we try to do here, what we try to address here, because what we try to focus here, actually, I'm not explained in a detailed manner. Maybe I'll take the sequence diagram. It will be much more detailed because okay. Actually, what we try to do in a real case, when a data demand is done, the submitted all the vehicles consent, okay, NFT is created, good, encrypted bid, accepting the bid, and transfer to escrow, good. Then, okay, the real case, the issue starts here. The vehicle accepts certain conditions. For example, in radar, it accepts certain conditions and starts to data collection. And then once it completes the data collection, it then uploads a data with proof. The proof, what we assume here, is basically the integrity of the data. At a certain point of time, I have a certain the contents of the data, and I upload it at a certain hash. That represents the integrity of the data. It just to complete, it starts with like that. So it starts, each vehicle uploads this data to the vehicle OEM. The vehicle OEM gets the data and the proofs are reported in the blockchain. Vehicle OEM, what he does in the normal case, what we consider here, he gets all the data, he does some privacy to conceal the data, which does some anonymization on the data, basically to clean the data as required by the radar OEM. And then he gets the final state of the data processed. He then submits the proof as well. So you have basically two sets of proofs, one from the radar vehicle OEM, as well as multiple proofs from the vehicles. So, and then this data is then uploaded to a external database or data pool, and then the OAuth is generated for the radar OEM to access the data. Once he starts to use the data, he will then report a review. Actually, a review is with respect to the data, and then if he submits a review as bad, then the bidding process itself is stopped here. It's not, if the bidding, that is one case. And if he stops the bidding process here, then the vehicle OEM will be aware of the lack of integrity in the data. Then he starts to verify each data along with its integrity from each of the hashes and also the raw data. And then it will be able to identify the vehicle which has reported malicious or wrongly forged data. This is one case that we can do at the blockchain level. But there are certain cases, there are loopholes at the there are certain loopholes which are not which can occur.
Okay, I have done two questions based on your answer. First of all, I'm not sure what you call data integrity proof from the vehicle. That's why I would like to know more. And second, I'm not sure also whether you can perform a review determining the attack on the integrity from the attacker on the left. Why it wouldn't be something performed by the
vehicle OEM?
The vehicle OEM, yes.
Yeah, I mean, if he wish, normally the use case we have designed. Yeah, actually, you're correct. Use Rudy. So correct. If it's preemptive, yes, it should be avoided at this level in order to verify the data.
I mean, especially if the data are cooled in some way, anonymized or whatever. But,
yes.
But what do you call data integrity?
Data integrity, in my case, I've understood it as a simple case. Like, for example, the raw data at any point of time where the vehicle uploads, it's basically hashed in order to prove that it's a state at a particular point of time. The data state is at a particular point of time is this.
Okay, but this is only some protection against attacks over the communication channel in that case.
Not communication channel.
It doesn't prevent compromised vehicle from reporting bogus data.
Yeah.
So
you can report bogus
data. My point
was,
can you make the economy of, for instance, remote attestation, some form of remote attestation, and in this overall protocol, if you want to ascertain that the data cannot be tampered with.
Exactly. Okay. This remote, the remote attestation, it should be embarked inside the blockchain itself as a smart contract in order to verify the integrity of the data. Because that is one case. That is one case that we can we need to take into account.
And then one question is, okay, what happens if you anonymize part of the data? What do you need to do in that case to integrate the remote attestations within the overall picture?
Okay. Yeah. Okay. Good point. Actually, yeah, it's a good question. Actually, like, for example, like the ideal thing with Substrate is like we are not limited to implement all the logic of, for example, that we have different techniques of data reviewing, like the remote data reviewing. So all these techniques can be offloaded from the blockchain we can automate all these transactions to an off-chain execution, basically an API, external API, in order to get the proof in an automatized way. Although we depend on centralized systems for determining the veracity of the data or the integrity of the data, the remote verification, because the smart contract is somewhat limited to perform this task. So there's actually an off-chain component that we can design in order to verify in order to offload the data to an off-chain component, external component, which is agreed upon by all the actors, which decides the integrity of the data, and then it's reported back to the blockchain, and then the blockchain can pick up the data, and then it can perform the rest of the process. So that is one thing which lacks. Does it answer your question?
No, I see your point. Okay. That's the way to deal with the problem.
Okay. The second question was more on the privacy concerns. The privacy concern, like here we take the simple case of anonymization of the data, which is highly sensitive. So, which does not reveal in any kind of the vehicle's direct information. And for example, the location or any other personal details or GPS details, for example. But here these some kind of the objective of is to respect the GDPR, as we have certain constraints in the term of pseudonymization of the data and the right to be forgotten. So, for example, if the vehicle later tries to retrieve the data which it has already shared then we should be able to pseudonymize the data, and also the right to portability of the data. So all these are some things which we try to address here.
Now, another question about that that use case, maybe a bit more provocative in a way. Okay, so you have this protocol for exchanging and monetizing data. But who's exactly monetizing the data? Who owns the data? I mean, if I'm a driver, do I own my car's data? And is there, in that case, is there a way to integrate, for instance, the fact that I'm willing to share that data within the protocol?
Yes.
Did you consider that possibility?
Yeah. Yeah, I think with the advent of GDPR, I think before the advent of GDPR, I think each one did in their own fashion, like because there were a lot of documents for us to give the consent. But after the advent of GDPR, I think the OEMs have to respect the privacy concern, and that is more like another, I think, horizontal, which works on all the different use cases. So basically, what happens is like the system which is to be designed, basically it should respect the privacy by design. Basically, it should be more fluent to the user in order to understand that his data is going to be monetized, because he is the owner of the data. Ownership of the data is with the vehicle, and the ownership of the data always resides with the vehicle. He gives the consent to utilize the data, and I think he has the ownership even to retract back the data. For example, the portability of the data states that if in case if in case I want my data back and I want to reutilize it for another service, I should have the right. So I think.
But for instance, I mean, just to make my question a bit clear,
Okay.
Do you consider that, okay, I would give access to all my data on the car, or not at all? Do you consider the car is the boundary, or do you consider that any data retrieved through that protocol would be fine because the vehicle cares? But then my next question would be, what if the vehicle is compromised, for instance, somehow, and data get leaked, despite the will of the driver, without his consent? Is there a way to integrate that consent about some particular data into the protocol?
Yes. Is there a way to integrate? Yeah, the data consent.
I think it's probably close to my question about the platform integrity. So making sure that the platform is not compromised when it reports data.
Okay.
In terms of integrity. But maybe that's a similar question, but with some more privacy oriented. Okay, so I guess probably if there's an answer, it should be integrated into the protocol in similar ways.
Yes. Yeah. Yeah.
Okay.
So
maybe I should move on.
Okay.
Because there may be other questions from my colleagues.
Okay.
I would like to raise a question now about the other use case, the certification use case.
Yeah.
And there I was really wondering what was the motivation to use the blockchain-based certification in comparison with a more traditional centralized distributed, but authority-centric
Exactly.
database, where you would have an authority in charge of the certification, even if it's distributed for performance and for addressing the distribution of the application. I was wondering if there was any rationale that was due to reusing the infrastructure that you deployed, maybe for use case number 2, that may be one reason, so that you don't have to create another infrastructure for that, or what's the rationale, and does that really solve the problem in the economically viable way compared with the traditional solution?
Thank you. Okay. That
Okay.
the questions, the whole spectrum. Yeah. Actually, actually, there are a lot of centralized systems which really works very fine. Like it's totally automated. Like for Belgium and Belgium has a car parse and works fine. It's adopted by, I think, almost all the users. But what there are other propositions as well for this simple problem, like to certify the data. For example, the hash of the data can be stored in the blockchain, and the data, the real contextual data, which corresponds to the hash, is stored in a separate distributed database. Like it's a distributed database, like in traditional sense, or in the case of decentralized distributed database like IPFS or Swarm. So normally it's another perspective, like where we have maintained the contextual data on one hand, we have the proof which resides in the blockchain. That is what
certification is performed using the blockchain.
Yes, exactly. There's one perspective that we had experimented, and then it seemed a bit complex to handle. As you said, it seemed a bit complex to handle either a database distributed or a decentralized database. In addition,
I mean, maybe to rephrase my question, in use case number 2, you have multiple parties taking part into the transaction, the monetization, clearly. So that's perfectly fit, no problem. But in this application, okay, you have an authority or consortium who's responsible for certifying the data.
okay.
So is that a situation where you really need a blockchain?
Exactly.
Apart from reuse?
Yeah.
Again.
Actually, yeah, it's exactly the point. Actually, I wanted to precise as well. Like the notion of putting in admins is basically an additional level of consensus which we put, actually, apart from the validation. Like the only validation that we can perform on order meter data is like it's usually in incremental fashion, because it does not, the tokens which are deposited should stay in the vehicle account. It should not diminish. So it should always increment, and it should increment only if the transaction is valid. Like, for example, if only the client API, because there's an advantage, because in Ethereum, actually, we deploy an external client API, which sends the transaction and which performs the validation. The client API can be subjected to attacks. It is external to the blockchain system. It does not perform any on-chain validation. So the point I would like to precise here is that that's why we needed an admin, but an admin is just an extra layer of security which you have put in place. Normally, in the smart contract that I've developed, actually there are 2 cases where we can allow any transaction which is valid to be automatically increment the NFT tokens, or it should need a certain amount of admin signatures as transactions for a particular request for an NFT. So that is 2 cases that I tried to do, but I found the first case actually for each transaction for an admin to send his votes to be kind of cumbersome. So I'll go with the automated validation. That is the only reason I did that, but it was just more to experiment. But I would prefer the automated way with admins, just to maintain the blockchain layer consensus, and a smart contract to decide to transfer the NFT tokens or not.
But that's mostly related with the use of the smart contracts.
Exactly.
Okay. Okay. I think I'm done.
Okay.
Thanks.
Thank you.
Okay, thank you very much. So now we will, we had the 3 rapporteurs, so now we'll go to the rest of the jury. I propose to start with Madame Christine Hennebert, who's remote.
Bonjour. Pour commencer, je voudrais féliciter Cyril pour son travail. Je le suis depuis le début de sa thèse à travers le comité de suivi individuel, et je dois avouer qu'à chaque étape, il a fourni un travail assez gigantesque, et je salue l'effort de démarche scientifique à travers tout le travail qu'il a fourni depuis la première année, et notamment le travail d'implémentation d'état de l'art que l'on ne voit pas dans toutes les thèses et qui donne un réel retour sur expérience pour pouvoir vraiment valider là où il y a des points qui ont besoin d'être creusés. Et derrière, il propose une solution qui me paraît très, très pertinente, très intéressante pour le domaine de la blockchain et des consensus.
Merci, Madame Christine.
Alors, au regard de votre exposé, alors moi j'avais une première question parce que donc sur l'introduction du protocole Cuba, il est notamment motivé par le fait qu'il passe à l'échelle, donc la propriété de scalability. Et dans la littérature, c'est le protocole CLIC qui est le meilleur sur ce sujet-là. Et je me suis demandé quel est le besoin de scalabilité, de passage à l'échelle au regard des cas d'usage que vous avez considérés.
Ah oui. Ok. Oui, c'est une très bonne question. C'est que, oui, il y a plusieurs choses pour dire pour ça. Oui, je vais switcher. Oui, ok. Oui, switcher en anglais, s'il vous plaît. Okay.
Yes.
The first, I think in all the tests that we have noticed, like starting from the use case until the different two use cases and all the implementations, I mean the blockchain propositions, we have remained at a level of 25 nodes, and we have not progressed beyond 25 nodes. I mean, not progress in this case, like we have taken a consortium to be at most of 25. That is, I mean, that is not a secure figure, but that is somewhat our assumption. So that is one thing that I would like to confess. I mean, that is one assumption that we did, because our thesis proposition, thesis was most limited to consortium blockchain consensus algorithms. If we, the point to address in terms of scalability, why? Because in future, for example, if we have a bigger consortium, for example, 100 participants, like in the modest sense, I'm talking, like from private blockchains, we should be able to accommodate the consensus protocol. Or in the case of interoperable blockchains, for example, which extends to multiple chains, we need some consensus protocol which would validate all the chains with the multiple actors at the inter-blockchain level, even at the single chain level. So we need some kind of consensus protocol which would be scalable with the number of messages it can send and receive. So that is one perspective that we held in future. That is the reason why we wanted to address scalability by first there are many things to address the scalability. The first basic thing is basically the consensus protocol at the level of transaction processing, because there is a recent work by in DAG. Basically, the DAG, basically what they propose is basically take advantage of the mempool. What they did in mempool is basically to have multiple worker threads, and each worker thread was working on a particular part of the data. And there was a primary thread which was working on the header data. So they try to address the scalability in terms of the memory pool structure. So that is one significant work which presents a lot of transactions per second, like 70,000 transactions or more than that. That is astronomical work, which is claimed in the state of art. So that they try to solve, and on top of that, they build other protocols. But that is the base layer that they wanted. The only point they wanted to address is basically some nodes are idle during the consensus process. For example, a leader takes most amount of computational work compared to the other nodes. So so they try to address by uniformizing, homogenizing the work between all the nodes. They try to split at the mempool level, and then they try to improve the communication complexity, like in PBFT, EBFT, or QBFT. So they try to address the two perspectives. Our thesis also had a focus on that levels. I mean, our thesis like handles from the perspective of consensus, the scalability, and also in terms of the transaction processing, because once the transaction reaches, it is then redistributed in non-duplicated fashion to each quorums, and each quorums can perform the block proposition in parallel way. And also, they are not dependent on the previous block. They're not dependent on the chain of blocks to progress to a successive round, because they store the intermediate block in the ephemeral chain, and then they continue with the future propositions. And once the ephemeral chain is filled, then they continue to the interquorum, and then it's kind of pipelining. You can have multiple unfilled ephemeral blocks also. So we try to address in those two ways the problem of scalability. But when comparing it with Click, Click actually the protocol itself is very light. It is very, I mean, the block period, time period, what we tested is basically the least. It is like 2 seconds for every block proposition. And this introduced a lot of force. So we take the worst, I mean, the best case of Click in order to compare our Cuba protocol. So, so I think the time period itself is very short for Cuba, for Click to compare. So basically that had a better scalability due to these reasons. This 2 seconds is quite a less number actually, but we wanted to address the we wanted to identify the bottleneck actually. So that is why we did it. Yeah, but scalability, yeah, for those perspectives, like for example, interchain communication, interoperable chains, as also in case of sharding or extending it to the enterprise open source adoption, we had some certain things in mind. So that's why we want to do it. Otherwise, consortium can stay at a modest 15 or 25 nodes.
Ok. Et dans l'implémentation, dans l'usage qui va en être fait dans l'industrie automobile, comment, qui va porter les nœuds validateurs? Est-ce que ça va être un nœud validateur par entreprise automobile, ou enfin voilà, comment ça va se répartir?
Oui, oui. C'est une bonne question actuellement. Le ownership, oui. C'est normalement le véhicules qui participent. Normalement,
Okay.
ils vont juste participer avec une adresse, avec une clé privée ou publique pour interagir avec le blockchain. Ils ne vont pas participer dans la validation, dans le consensus, ou même bien participer dans la validation de transactions lui-même. Mais il va juste bénéficier de la blockchain infrastructure. Pour répondre à votre question, c'est normalement le OEM, il doit pour sécuriser, par exemple, normalement, même l'interconnexion entre différents OEM, c'est vraiment une question ouverte. On ne peut pas avoir d'accord entre les différents OEM. C'est vraiment un challenge parce qu'ils ne veulent pas diffuser les informations confidentielles avec un concurrent. C'est vraiment une question. Par exemple, si quelques OEM a identifié un partenariat consortium avec, comme par exemple, ici, on considère radar OEMs, par exemple Bosch ou Continental, si ils sont d'accord, toute la data va résider dans une infrastructure distribuée, maintenue par le consortium. Je pense que ça doit être réparti vraiment comme ça. Oui, mais après, le cas de différents OEMs, je pense que ce n'est pas une possibilité en réalité. Oui, c'est ça.
Okay.
Mais après, oui, c'est ça.
Donc la voiture, en fait, c'est un client léger et qui va interagir avec une infrastructure qui est portée par les constructeurs automobiles. Et aujourd'hui, cette infrastructure, c'est pas encore défini comment elle va être répartie entre eux, en fait.
Oui, c'est ça. Et après, il y a certains protocoles comme Ocean Protocol, ce que j'ai mentionné. Il y a si les véhicules peuvent participer directement sans avoir d'accord avec le véhicule OEM concerné. Ça, ils sont déjà faits. Ils veulent monétiser directement avec le market, le data market. Mais si on passe par un véhicule OEM, si le véhicule OEM, ils veulent bénéficier de sous, de commission, mais je ne pense pas qu'il va faire comme ça. C'est ça.
entendu. Alors, ma question suivante, elle porte sur le simulateur que vous avez développé. Alors, j'ai compris qu'il était développé en langage Java et je me suis demandé, dans la réalisation des expérimentations, la plupart des protocoles open source que l'on trouve sont dans d'autres langages. Par exemple, Click est en langage Go. Comment ça s'interface? C'est-à-dire que vous avez une couche en Java qui ensuite va pouvoir appeler les différents protocoles que l'on trouve dans Hyperledger Sotus ou Go Ethereum,
Oui.
qui sont dans leur langage natif. Ou bien vous avez réimplémenté ces protocoles dans votre simulateur?
Oui, oui, je vous explique avec un slide. Je vais trouver un slide. Oui, oui, pour expliquer un peu sur l'implémentation, oui, ça c'est juste un high view. Mais après, ce qu'on a développé, c'est on a développé la base de la simulateur. Mais je reviens vers la question pourquoi on a sélectionné Java. Mais avant, je vais éclaircir un peu sur la question de comment on implémente les différents protocoles. On a construit un simulateur qui simule blockchain Rousseau avec certains modules, packages, crypto, API, chain, network consensus, etc. Ce qu'on a décidé, la première chose, c'est pour rendre ça comme un simulate design pattern. Par exemple, pour changer juste le package ça, mais après le reste va être la même chose. Parce qu'on voulait juste, parce que le logic, le data structure, le logic de network, le logic de API, crypto, ça va rester la même chose. Mais après, chacun a choisi une différente manière de développement. Par exemple, QBFT, IBFT. Ils ont choisi Java. Ils ont choisi Bouncy Castle pour le hashage. Ils ont choisi, peer-to-peer, je ne rappelle plus, un libraire différent. Click, ils ont choisi Go. PBFT, ils ont choisi Python. Mais notre intérêt, c'est pour homogénéiser tout le développement avec un seul simulateur. C'est pour ça qu'on a reconstruit le consensus module plusieurs fois pour accommoder PBFT, Click, PBFT, QBFT. C'est juste changer le package ça. On a pu mettre le protocole de PBFT, Click, PBFT, QBFT. On n'a pas interfacé avec le vrai Ethereum protocole ou le vrai Hyperledger Sawtooth ou vrai QBFT, IBFT. On a resté tout dans la simulation, ce qu'on a fait.
Très bien, oui, entendu. Sur ce transparent, je me suis posé la question au niveau du module de crypto. Alors, j'ai deux questions, en fait, deux sous-questions. La première, c'est sur, vous faites apparaître des briques de chiffrement, déchiffrement, encryption, decryption. Et je me suis demandé, en fait, à quoi ces fonctions servent au niveau de la blockchain et notamment du consensus.
Ah oui, madame, oui, je cherche un slide juste pour montrer en détail sur la...
Parce que la blockchain, généralement, elle ne gère pas la confidentialité.
Ah, oui, oui, oui. OK. La raison pour utiliser le crypto, c'est pour vérifier, oui, c'est juste pour préciser ça, oui, c'est juste pour montrer le spectre. Je vais vous répondre à votre question aussi. Oui, c'est ça. Oui, c'est ça. Oui, ça, oui, c'est un niveau crypto. Ce qu'ils ont utilisé, c'est elliptical cryptographie par le Ethereum et Edwards curve par le substrate. Nous, on a utilisé RSA. et aussi pour le hashage K4 et Blake, et de P2P for Ethereum, le P2P for Substrate. L'intérêt pour utiliser une encryption-décryption dans le monde de blockchain, c'est pour identifier le node qui émet la transaction, qui, par exemple, dans le public, c'est vraiment important. Pour le privé aussi, parce que nous, on différencie, on fait la différenciation, on fait la différenciation entre le validateur et le non-validateur qui participent dans le network. C'est pour ça, toute la transaction qui émet, on va vérifier avec le public key pour valider la transaction. C'est pour ça qu'ils ont utilisé l'incryption et décryption. Et après, si le client peut participer, il va juste générer un compte, il va participer dans la transaction. S'il doit participer dans le consensus, il doit vraiment être éligible dans le process. Par exemple, c'est pour ça qu'on a fait une différenciation aussi dans le simulateur, on a fait une différenciation entre le validateur et le non-validateur. Et oui.
Oui, mais vous êtes d'accord que ça se joue au niveau de la cryptographie asymétrique, la différenciation par la vérification de la signature numérique, en fait. Donc, ça va être la crypto RSA qui fait ça, de ce que je comprends.
Oui, oui, c'est ça exactement ce que j'ai fait.
D'accord, ok. Ok. Et, alors, j'avais une autre question, c'est au niveau. Alors, vous dites que Click est sujet à des deadlocks, en fait. C'est-à-dire qu'à un moment donné, la blockchain ne sait plus comment choisir le leader, en fait, et donc comment ajouter le nouveau bloc. Et je me suis demandé comment vous évitiez ce problème dans Cuba.
OK. Le problème, OK, oui, madame. OK. Le problème de deadlock, oui, c'est vraiment un grave problème parce que c'est pas vraiment le fort. OK. Si bien, OK, à niveau de click ou à niveau de Babe ou Aura, il y a des protocoles qui résoudent le forks en utilisant le Grandpa ou Ghost protocol. Il va décider la chaîne qui est le long avec le plus de primary blocks. Ça, c'est OK. Mais après, ce qu'on doit compter aussi, les autres chaînes qui est créées, parmi les autres chaînes qui est créées, il y a des chaînes qui est malicieux, qui est honest aussi. Il y a des blocs qui est honnête aussi. Ce qu'on va faire pendant la résolution de la forks, on va choisir une seule chaîne. Aussi, on va virer les autres chaînes. On va juste supprimer les chaînes. C'est ça la réorganisation fait en Ethereum. Oui, en substrate, ce que j'ai appris, c'est pas vraiment virer, il va réorganiser le Hornet bloc. Mais après, ça vraiment en computation, en complexité aussi. Pour réorganiser un long chain, réorganiser le bloc, c'est vraiment un problème. Ce qu'on a fait en Cuba, c'est, OK, normalement, c'est à cause de deux blocs au même niveau. Et après, ça va continuer comme ça. Il va créer une chaîne, il va avoir plusieurs blocs au même niveau. Ce qu'on a dit, on a fait, c'est dans l'intra-quorum, on fait vraiment une compétition. On fait vraiment une compétition en disant, on crée deux blocs. Mais deux blocs, ça va être un partial block proposer qui va faire une compétition quelque sorte pour produire deux blocs. Et parmi les deux blocs qui est diffusé, qui a eu le threshold de votes, ça va être conformé. Ça, on fait une préemptive chose pour éviter ça. Après, le problème de fork, c'est plus ou moins lié avec la synchronisation avec les différents nodes. Si le chain il n'est pas consistant, si le node ils sont pas ils ont pas synchronisé, ça va créer des forks normalement. Ce qu'on a fait pendant la liveness aussi, le heartbeat, on fait la calculation pendant le reorg, pendant la reproposition de quorum, on fait la calculation à partir de heartbeat. Heartbeat, c'est un facteur crucial. Si quelqu'un n'a pas émis le heartbeat, on va suspendre pour une particulière époque. Ça, c'est un cas très sensitif. Mais après, on mesure quand même, on peut deviner quand même le liveness de la node. Par exemple, la participation à l'intra-quorum level, on peut même deviner à partir de utilitarian score vraiment le liveness quotient. C'est ce que comment on fait un préemptive chose pour éviter le problème de forks. On ne fait pas posteriori comme le grandpa ou on fait a priori, mais on ne fait pas posteriori comme le grandpa ou ghost. Parce que ça, c'est vraiment une perte de calculation, perte de temps et même, par exemple, la perte de data. Par exemple, transaction, ce qui est honnête, peut être viré aussi. Si c'est tombé dans une chaîne qui n'est pas finalisée.
Ok. Et est-ce que vous avez eu l'occasion de faire des simulations sur clic pour savoir dans quel contexte il y avait un deadlock?
Clic, OK. Pendant le test ou pendant la simulation, vous voulez dire?
En fait, donc, moi, ce que je comprends de vos travaux, c'est que en fait, clic est sujet au deadlock et que vous avez testé différents niveaux de passage à l'échelle, donc de scalabilité, donc en rajoutant des nœuds. Et ma question, elle porte si vous avez pu expérimenter si ce problème de deadlock apparaît je dirais globalement, dans quel contexte il apparaît en termes de nombre de nœuds et de passage à l'échelle? Est-ce qu'on
OK.
le voit tout le temps ou est-ce qu'on le voit dans certaines configurations?
OK, c'est une vraiment très intéressante question. OK. Un deadlock, c'est normalement, on doit résoudre, on doit résoudre le clic, c'est implémenté avec un deadlock resolution protocol, fork resolution protocol, s'appelle Ghost. Ce qu'il va faire quelque chose, il va choisir une chaîne qui est longue, mais pas avec une proposition de bloc, in block proposes. Normalement, il y a deux choses. Il y a deux propositions, types de propositions, in block proposes, out of block proposes. Il va choisir une chaîne qui a plus de in block proposes. Mais comment le deadlock arrive, c'est même le ghost, il ne peut pas résoudre le problème. C'est s'il y a des chaînes, par exemple, s'il y a 6 nodes, et s'il y a 3 nodes qui participent dans une chaîne 1, et s'il y a 3 nodes qui participent dans une chaîne 2, c'est vraiment un deadlock parce qu'ils ne peuvent pas résoudre le problème. Ils ont un state différent de les autres. C'est pour ça, chacun a un state différent. Il ne peut pas arriver à conclure c'est quoi le chaîne, le véritable chaîne. C'est comment? Mais j'ai concentré surtout sur le get. Ouais. C'est ça.
Ok.
Mais après le deadlock, le, ouais. Après le deadlock, le problème c'est on ne peut pas progresser la chaîne aussi. Ouais.
Et juste une dernière question. Dans Cuba, est-ce que, je dirais, comment vous gérez l'ajout d'un nœud ou le départ d'un nœud? Et notamment, est-ce qu'il y a un mécanisme qui permet d'éviter qu'il y ait un gros volume de nœuds qui partent en même temps? Et enfin, mon raisonnement, c'est le suivant, c'est si on a beaucoup de nœuds qui vont arriver en même temps, ils ne font pas partie encore d'un quorum, puisqu'ils sont, on va dire, nouveaux. S'il y en a beaucoup qui partent en même temps, ils peuvent aussi faire en sorte que les quorums fonctionnent moins bien, parce que typiquement, ils vont être moins fournis en participants. Et est-ce qu'il y a un mécanisme qui permet de gérer les arrivées-départs pour éviter qu'on se trouve dans ce type de situation?
Ah, OK. Oui, c'est vraiment une bonne question. Oui, mais après, OK. OK. Nous, on a focalisé sur un aspect consortium en disant que le node, il va toujours participer, mais dans le cas de public, ce n'est pas le cas. Normalement, c'est pas le cas. Mais si on veut extender un peu sur le public, il faut. Mais après, le problème avec le public aussi, si on ne participe pas si on ne participe pas, on va perdre le utilitarian score aussi. Mais ça, c'est plus ou moins, c'est une score qui est grâce à consensus process. Mais maintenant, si on est vraiment, par exemple, si on est malicieux, on n'est pas, oui, je vais juste switcher en anglais. Si we are malicious, the node is malicious and he does not want to participate on purpose, then we can identify. If he wants to voluntarily depart, then it's another problem. I mean, okay, the quorum does not change automatically, the number of quorums. The number of quorums are configured like in Genesis, like in any other configuration of blockchains. Like in Genesis, we decide the number of quorums, we decide the number of participants who can participate as validators or non-validators. The dynamic arrival and depart is something I think we need to consider. I think I mentioned in my report, but I'm not sure if I mentioned this statement. If I'm not sure, if there should be, I mentioned the aspect of dynamic quorums, like where we can, where it's not necessary to have a large number of quorums. We can just choose a small subsample of quorums to maintain the consensus. I think I mentioned it in the perspectives. Yeah, that was one thing I mentioned, but yeah, that was another aspect as well. But yeah. I think the dynamic quorums to either increase or decrease the number of quorums based on the participation rate in the network. I think yeah, I think we need to take into consideration. But other dynamic quorum from the other aspect, for example, as we know, the quorum is the exchange, message exchange within the quorum is the most demanding, is a highly complex communication complex. So what we'd like to propose is, like, in perspective, is like taking into utilitarian score. We would like to form dynamic quorums, not like 2 or 3 or 5 quorums, just form a simpler number of quorums to just base the consensus process and choose a new set of quorums for a new epoch, like a least recently used algorithm, new set of quorums for a new nodes which can participate, which have not participated in the previous epoch. Something like that is I made in the perspective. But that's a nice point that you have mentioned. Actually, yeah. For public networks, it is really the case where nodes can leave, participate at will.
Okay. Merci beaucoup. Merci pour la réponse à mes questions et encore bravo pour ton travail.
Merci, Madame Christine. Merci pour vos retours. Ouais, merci.
Merci beaucoup. Donc, je passais la parole à Madame Pascal Guiton. Patricia Guiton, de Renault.
Merci beaucoup. Alors, j'ai pas de questions pour toi, Cyril. Pour toi. Juste de noter que c'est un travail qui est énorme, qui est très conséquent. Il y a eu un état de l'art énorme qui a été fait et on l'a vu, hein, on peut interpréter différemment. On a chacune des questions, on l'a vu également amener d'autres questions et c'est le problème un peu de la blockchain, que l'état de l'art de la blockchain est très mouvant. Tout évolue très très vite, il n'y a pas de maturité et dans ce cadre-là, c'est quand même assez compliqué de faire une application industrielle et puis même de faire de faire une thèse, de figer des choses. Et ouais, je voulais juste mentionner un petit peu cet état de fait et pour nous, tu as très bien résumé, tu as réussi à structurer des choses qui partent un peu dans tous les sens. Et de même que quand je dis des questions à tiroir qui en amènent d'autres, c'est le propre du travail que tu as fait. On a envie d'aller toujours un peu plus loin. Bon, ça va être compliqué avec Renaud, mais oui, je pense que ça ouvre pas mal d'ouvertures scientifiques et en ça, merci beaucoup pour ton travail.
Je vous remercie. Non,
je vais arrêter là.
Merci beaucoup. Et donc, après, je vais passer la parole à Séverine Glock, qui est commencé.
Donc, moi, pareil que Patricia, je ne vais pas te poser de questions. Je pense
Vous
que je t'en
pouvez
ai posé
poser.
assez pendant 3 ans. Non, je voulais te remercier pour la qualité de ton travail et l'implication que tu as démontrée pendant ces 3 années, qui n'ont pas été faciles, à mon sens, puisqu'on a eu une période de Covid et tu es tombé dedans. Donc, faire une thèse dans ce cadre-là, c'est pas évident, surtout quand on arrive. Et le deuxième point, c'est aussi que tu as fait face à une situation chez Renault qui n'était pas simple, dans le sens où on a lancé cette thèse parce qu'on avait un projet qui était porteur, et ce projet s'est arrêté pendant ta thèse. Donc, le cadre applicatif de tes recherches a été interrompu. Même si aujourd'hui, les cas d'application qui ont été traités au travers de ta thèse restent quand même valables. Ce sont 2 cas qu'on regarde toujours et qui vont être des cas porteurs pour l'avenir. Donc, le cas de la data certification, c'est un cas d'usage qui s'applique à tout ce qui est accidentologie, donc dans le cadre du projet SIM. Et c'est l'avenir de ce qu'on appelle, nous, chez Renault Mobilize, usage-based insurance. Donc, ce domaine, on va dire, de business va évoluer, doit se transformer, et la blockchain pourra s'appliquer ou non. Mais en tout cas, c'est un vrai cas d'usage. De même que la data monetization. Aujourd'hui, l'avenir, c'est le partage des données entre acteurs qui n'ont pas l'habitude de s'échanger des données pour construire de nouveaux business cases. Donc, c'est vraiment 2 cas d'application on verra dans les années qui vont venir comment ils vont être résolus. En tout cas, ce que tu nous as proposé ici est une piste de solution. C'est pas la plus simple, parce que dans une entité comme Renault, c'est une vieille compagnie qui a besoin d'évoluer et de se transformer, et elle n'est pas encore prête à accepter une telle transformation, parce que ça touche beaucoup de domaines, en fait, notamment des domaines organisationnels qui sont très longs à transformer, en fait. La technologie a beau être complexe, elle est peut-être plus facile à mettre en place que les transformations organisationnelles. Donc, voilà, c'est ce que je voulais souligner. Et merci beaucoup pour ton application au cours de ces 3 ans.
Non, c'est bon, merci.
Merci. Je passe la parole à François Verdier, qui est le directeur de thèse.
Merci, Monsieur le Président. Je ne sais pas. J'ai quand même une question et je la poserai à la fin. Mais ce que je veux dire, c'est qu'effectivement, tu as fait un travail absolument gigantesque. Tu as forcément, et Séverine l'a dit tout à l'heure, tu as passé le Covid, les 2 années de Covid, on va dire ça comme ça, pendant tes 2 premières années de thèse, et tu as eu en plus un projet Renault qui a été arrêté, donc c'était pas facile du tout. C'était très difficile, et j'avoue que moi, j'étais pas très rassuré de t'encadrer en thèse pendant ces moments-là. C'était pas tout à fait facile. Et pourtant, tu as fait un excellent travail. Tu as été, je pense, l'un des étudiants les plus respectueux, les plus sympathiques, les plus les gens qui te remercient en permanence, c'était toi, c'était voilà.
Non,
Et tu as fait en plus un travail absolument monstrueux. Ta thèse, c'est le meilleur exemple parce qu'elle est lourde. Elle est lourde parce que j'ai fait pas mal
oui.
enfin,
On a
des
fait pas mal de
non,
corrections.
je t'ai indiqué les corrections. Au départ, c'était 478 références. Bon, non. Et tu as fait une thèse magnifique, et tu as fait en plus un travail qui est cohérent, depuis le début de ta thèse, enfin, depuis le début de ce que tu nous as montré, de ce que tu as rédigé, c'est tout à fait cohérent jusqu'à la fin. Donc là, je me permets de te remercier et de te féliciter sur ce que tu as fait. J'ai quand même une question,
Oui.
finalement, mais ça va être relativement rapide, je pense. Je me demande quelle serait la première des perspectives qu'il faudrait adresser dans ta thèse. Il y a plein de perspectives et tu l'as compris avec après toutes les questions qu'on t'a posées, il y a plein de perspectives différentes dans différents domaines. Je me demande, quelle serait la première perspective que tu verrais dans ta thèse?
Ok.
Et rapidement, hein, c'est pas la
Oui,
peine
oui.
de...
Non, non, non. Ah oui. Ce que j'ai toujours dans mon tête, c'est comment j'ai déjà contacté, je ne me rappelle plus, c'est un fork de Ethereum ou je ne sais pas quoi, pour, pour, euh, pour proposer le consensus, comment
Ok.
c'est évalué dans un monde open source.
Oui.
Comment, c'est quoi comment on peut mettre dans un comme un get ou bien un substrate, un choix comme un consensus algorithme. Même s'il y a des limitations, il faut juste raffiner un peu et pour mettre dans le vrai blockchain, ou même il y a un certain temps, oui, il faut avoir un certain temps pour ça. Mais oui, c'est ça que je pense, c'est la perspective, il faut que je prends parce que les autres perspectives, oui, ça va complémenter, mais après, oui, ça, je pense, il faut juste
C'est-à-dire que
proposer.
tu n'es pas certain de tes résultats, tu n'es pas absolument certain que Cuba soit meilleur que Click?
Non, non, c'est pas.
Ah non, je te pose la question. Hein.
Oui. Non, ok. Pour comparer avec Click, c'est, oui. Pour comparer avec Click, oui, c'est pas, oui, on a comparé les clics dans un cas très bon, avec 2 secondes, mais après c'est pour ça on a un courbe comme ça. Mais si on considère un cas normal, c'est OK, ça va. Mais je pense, ça c'est OK, je suis confiant, mais ça c'est juste pour le travail doit être un peu ouvert. On doit avoir un plus de critiques pour être mis en place dans la production quelque part. Si ça tourne grâce à notre étude, ça va. C'est une bonne contribution pour la société même. C'est recevoir ça. Et après, rien à voir avec la comparaison. Oui.
Très bien. Bon, merci. En tout cas, je te félicite de cette thèse que tu as fait avec moi pendant 3 ans.
Je vous remercie infiniment.
Je redonne la parole au président du jury.
Merci beaucoup. Du coup, moi, je suis le dernier, donc on a fait le tour du jury. Merci à tous pour vos questions. Donc, félicitations pour ton travail qui est conséquent et apprécié par les membres du jury, il me semble. Moi, j'ai juste une question rapide pour finir. C'était sur ton dernier slide, je crois, tu mentionnes que tu as remonté des vulnérabilités. Et
Dernier,
sur le
cap, c'est ça?
vers la conclusion, oui. Tu dis que tu as remonté un certain nombre de vulnérabilités. Et je voulais savoir, si j'ai bien compris, c'était dans des systèmes. C'était après, je crois. Non. Je pense que c'était tout ton dernier après les citations, non? Tu avais les papiers. Tu avais les papiers, tu listais les. Si tu continues. Suivant. Non.
Ah, ok.
Sur le dernier slide, je crois. Celui-là. Non, c'était pas là? Reviens un peu. Non, c'était contribution.
Peut-être sur la première planche.
Alors,
Avant les.
Ouais, je suis désolé. Il me semblait que tu disais que tu avais remonté des vulnérabilités, j'ai mal compris alors.
Vulnérabilité, oui, c'est ça. C'est ça la vulnérabilité.
En bas.
Open source contribution.
C'est
Pour
les
le
contrib-
à niveau get, click, and oui, c'est ça. Même parity aussi.
je crois que tu as mentionné la vulnérabilité. C'était des attaques que tu as remontées sur
Oui,
ces-
non, c'est
J'ai
pas
mal compris.
attaque, c'est-à-dire on a trouvé une vulnérabilité, on a fait un test. Le but, c'est on a commencé avec un test. On a noté plusieurs issues avec tout ensemble de Ethereum protocols. Et la première chose, le truc très grave, c'est le stalling à l'EVM layer parce qu'on a noté que certaines transactions sont bloquées. Ils n'ont pas résoudre à compléter parce que le node, il va émettre les transactions. Ça doit être validé par l'EVM et après, ça va remonter jusqu'à consensus pour être validé. Mais même au niveau de EVM, grâce à pprof, on a pu faire un debug sur le binaire. Et après, on a trouvé que le problème, c'est lié avec un EVM process. Mais après, on a reporté ça avec le graph, pprof graph, sur le open source. Après, ils ont acknowledgé. Ils ont dit qu'il y a vraiment un problème à niveau de caching, à niveau de EVM DB caching, de caching. Et c'est ce que, oui, c'est ce qu'on a reporté. Après, ils ont résolu le problème.
D'accord.
Et ça, c'est, oui, ce period one fork, c'est vraiment, c'est un fork. Normalement, on a essayé avec le 2 secondes. C'est ça le bon, le meilleur truc pour clic. On a essayé avec un seul seconde aussi. C'est pour ça qu'on a constaté plusieurs synchronisations problèmes. On a reporté cette erreur-là. Ils ont acknowledgé, mais ils ont dit que il faut avoir certains temps de synchronisation en mois, 6 secondes, en mois. Et ça, c'est et après, même avec 6 secondes, il y a des synchronisations problèmes. Et après, on a trouvé certaines issues sur le EIP 155. C'est vraiment, on a testé sur une blockchain privée. Pour distinguer avec une blockchain privée et blockchain publique, ils ont mis en quelque sorte de proof of proposal pour recouvrir, pour récupérer le public key. Mais après, le problème, c'est lié avec la récupération de public key parce qu'ils voulaient arrêter les attaques de replay. Par exemple, il y a certains membres, il y a certaines personnes qui fait un replay qui fait un replay d'une transaction d'une autre chaîne juste pour avoir en quelque sorte de bénéfice. C'est pour ça qu'ils ont fait ce proposal-là. Oui, on a trouvé certaines choses sur ça.
Et donc, c'est du coup, c'est des vulnérabilités sur le vrai Ethereum, pas sur une simulation.
Oui, c'est vrai, Ethereum privé.
L'impact était important sur les privés seulement.
Exactement. Mais oui, on peut, oui, mais après, le binaire, c'est utilisé, nous, on a utilisé pour une chose privée, mais le binaire, c'est commun. C'est pour le public et le privé. Oui.
Et du coup, ça s'est bien passé, la communication avec eux, parce que
Non,
parfois,
non.
la communication sur les reports de vulnérabilité, ça peut être compliqué. Non, ça a été...
Oui, oui, oui. OK. Ils n'ont pas répondu instantanément. Ils ont pris le temps. Mais après, l'explication, j'ai reposé les questions. Après, ils ont quand même analysé. Oui, c'est pas assez bien.
OK, très bien. Merci beaucoup.
Merci beaucoup, monsieur.
Merci pour la présentation.